If the story of how the world came to be, the best story ever told, isn't true, what then? The James Webb Space Telescope, which is the world's most powerful telescope for looking into space, wasn't just made to take pretty shots. That was the point, to prove what we already thought about the Big Bang, time, and the start of everything. However, what it found has completely changed the way we think about the universe. There are galaxies that shouldn't be there, stars that form too quickly, and structures that are too smooth to make sense. All of this makes me think we might be looking at the wrong origin story. This isn't just a change in science. It might change everything we thought we knew about the real world. A telescope that changed everything. For many years, scientists have been looking farther and farther into space in the hopes of seeing the universe's first light, which is thought to be a tiny signal from the start of everything. The Big Bang theory, which was the most popular explanation in astronomy for a long time, said that the universe began 13.8 billion years ago and quickly grew from a point called a singularity. From then on, everything, stars, galaxies, even us, has been a part of that flow outward. Images from Hubble and other telescopes showed us how the universe is growing and confirmed many of the things we thought we knew. Then, James Webb came along. The James Webb Space Telescope, JWST, was not designed to tweak a few details. It was built to peer deeper in time than anything before it, to capture the glow from the earliest galaxies and to witness the cosmic dawn, the moment when the first stars lit up the darkness. It took decades to develop, cost nearly $10 billion, and represents the most powerful space observatory ever created. Launched in December 2021, Webb promised to open a new chapter in our understanding of the universe. Few anticipated that it might close the one we thought was settled. As soon as Webb's first pictures came out, experts knew they were different from what they had expected. Yes, they were beautiful, but behind the golden glory of early galaxies and faraway stars were mysteries, contradictions, and structures that were shockingly adult. Big Bang models didn't see these as the chaotic young galaxies they said would exist. They were too big, too smooth, and sometimes too old. From the outside, it looked like they didn't belong there. It wasn't what the James Webb Telescope saw that shocked people the most. It was when it saw it. Models that are used today say that it should have taken hundreds of millions of years after the Big Bang for the first galaxies to form. But Webb found galaxies that were fully formed only 200–300 million years after that assumed start. They were also not weak. According to current theories of evolution, they shouldn't have been that big, moving and full of stars and elements that early on. As more data came in, a pattern emerged. Too many galaxies, too soon, too big, too organized. It wasn't just a question of adjusting a few numbers or adding a footnote to the standard model. It was the kind of discrepancy that threatens the core assumptions behind our entire cosmological framework. One astrophysicist described it bluntly: "These galaxies shouldn't exist." Another compared the findings to looking at a classroom full of full-grown adults, when you were expecting to see toddlers. These weren't the signs of a young, turbulent universe just beginning to take shape. They were signs of a universe that looked mature from the start. And so the question arises, what did we miss? Could our interpretation of redshift, the stretching of light that tells us how far away something is, be flawed? Could time, as we understand it on a cosmic scale, be playing tricks on us? Or is the very idea of a universe that began with a singular event simply wrong? The consequences are huge. Some of James Webb's data keep showing early structure and complexity where there shouldn't be any. This could be very bad for the Big Bang theory, not just requiring tweaks, but possibly needing to be replaced. That doesn't mean there was no beginning to the world, but it could mean that the start wasn't what we thought it would be. When or how? Or why? Some scientists are now whispering the unthinkable. Maybe there was no Big Bang. Maybe the universe didn't explode into existence. Maybe it always was. Or maybe it's part of a cycle, expanding, contracting, rebounding, in ways we're only beginning to imagine. There is no doubt that James Webb has already changed everything, not by disproving the Big Bang theory, but by giving us information we didn't expect, which is what great science always does. And only one can survive when opinion and observation meet. The universe doesn't care what we think will happen. It is what it is. Now that James Webb has found it, we can see it better and more clearly than ever. What James Webb was built to see. No, the James Webb Space Telescope is not just a follow-up to Hubble. It is a completely different type of tool that was made to answer questions that Hubble could never reach. Hubble looked at light in the visible and ultraviolet ranges. James Webb, on the other hand, was made to look in the infrared, which is an important wavelength for studying the early universe. It's a simple but deep explanation. As the universe grows, light from old galaxies gets redshifted, which means it gets stretched out into longer, weaker colors. You need to look into the long, cold afterglow of the past to see how galaxies, stars, and even structure itself came to be. That's exactly what Webb provides. Orbiting nearly 1 million miles from Earth at a gravitational balance point called L2, Webb sits in the cold shadow of our planet and its moon, shielded from the sun by a 5-layer heat shield as large as a tennis court. It operates in near-total darkness, allowing it to detect faint glimmers of infrared light that have traveled across more than 13 billion years of cosmic history. It is by design a time machine, not metaphorically, but literally. The farther Webb looks, the older the light it captures. But it wasn't just built to look far, it was built to look first. One of its core missions was to detect the very first stars and galaxies, a period in the universe's history known as cosmic dawn. This is the era following the so-called Dark Ages, a time after the Big Bang when matter had cooled enough for atoms to form, but before stars had ignited. Scientists hoped Webb would find the earliest flickers of starlight that eventually lit up the universe, the transition from cold, dark hydrogen clouds to hot, luminous structure. The expectation was to catch galaxies forming in chaotic clusters, their stars made mostly of hydrogen and helium, with little metal content. In essence, Webb was designed to confirm and clarify the Big Bang's aftermath by providing unprecedented detail of the very first light. It was also built to answer other long-standing questions. How do galaxies evolve? How are stars born inside clouds of gas and dust? Could we detect atmospheres around exoplanets? Webb's massive 6.5-meter gold-coated mirror, more than 2.5 times the diameter of Hubble's, was crafted to resolve these mysteries. It could not only detect dim, distant objects, but also reveal structure and detail in ways no telescope ever had before. The task brief was very broad. Scientists thought that if they could look far enough, they would see the early chaos that the Big Bang model predicted, baby galaxies that were just starting to form and had simple structures and odd shapes. They were hoping to see how complexity grew over time, which would support the timeline in which stars slowly made stronger elements. Galaxies came together by merging, and structure changed over billions of years. But that's not what they saw. The first images Webb returned were hailed for their beauty, but it was the data behind them that sent shockwaves through the scientific community. Instead of chaotic infant galaxies, Webb found massive, well-structured systems astonishingly close to the supposed beginning of time. Instead of early, metal-poor stars, it detected objects rich in heavier elements that shouldn't exist so early. Instead of watching galaxies build slowly from cosmic dust, we were seeing snapshots of what looked like fully formed mature structures existing when the universe was still a cosmic toddler. This wasn't a matter of precision or interpretation. The observations directly clashed with what Webb was expected to confirm. It did everything it was built to do. It peered back to the edge of the observable universe, captured the faintest infrared light, and resolved galaxies that had never been seen before. But in doing so, it revealed something else. Our theories weren't ready. We built the most advanced telescope in history to confirm our best cosmological models, and it may have instead started to unravel them. Every capability that was supposed to reinforce our understanding of the Big Bang now seemed to raise new doubts. The timeline of cosmic evolution appeared shorter, the structures more mature. The formation of galaxies and stars, once thought to take hundreds of millions of years, now appeared to happen almost immediately. To make things even more confusing, Webb was doing exactly what he was supposed to be doing. There were no noticeable mistakes in the system or in the tuning. Its sensors, such as NearCam and NearSpec, were making clear, complete views. It had perfectly lined up mirrors. The problem wasn't with the tools, it was with the idea. James Webb wasn't just peering into space, it was peering into our assumptions, and the light it returned brought with it the unsettling suggestion that maybe we were wrong, not about the data, but about what it means. What the Big Bang Theory actually says. In order to fully understand how the James Webb Space Telescope might be shattering our ideas about the world, we need to know what it is that it is challenging. The phrase Big Bang is used so often and in so many contexts, documentaries, pop culture, and classrooms, that its real meaning is often lost in the many ways it is oversimplified. The way most people think of it, it was an explosion, a huge cosmic blast that threw matter into space. That's not quite right, though. The Big Bang was not a space event. It was space itself exploding. The Big Bang Theory is a mathematical model of the universe's expansion. It proposes that roughly 13.8 billion years ago, all of space, time, matter, and energy were concentrated in an unimaginably hot, dense state. Not a point in space, but space itself compressed to near zero volume. And then space began to expand. Not into anything, but as a stretching of the fabric of reality itself. This expansion continues today, with galaxies not flying through space, but being carried apart by the expansion of space between them. There was strong evidence for this model. In 1929, scientist Edwin Hubble made the most famous evidence when he saw that light from faraway galaxies was redshifted, which means it was stretched to longer wavelengths. This meant that they were moving away from us, and the universe was getting bigger. Your mind will take you back to a time when the universe was smaller, denser, and hotter, until you hit a singularity. In math terms, that's what the Big Bang Theory is all about. Over the next few decades, more data supported the idea. Scientists found the cosmic microwave background radiation, CMB, by mistake in 1964. The CMB is a weak glow of microwave light that comes from all directions in space. This was seen as the cooled remains of the hot, dense early universe, which supporters of the Big Bang had forecast many years before. Then readings were made of hydrogen, helium, lithium, and other early light elements. The number of them was about right for nuclear fusion in the early moments of a hot universe that was growing quickly. All of this led to a remarkably successful framework, a universe born in fire, expanding ever since, cooling, and gradually forming stars, galaxies, and eventually life. The model worked so well that it became standard cosmology, adopted into textbooks, simulations, and global consensus. But despite its success, there were always gaps. The horizon problem was one of the issues. This is the question of why the universe looks so consistent when different parts of it should never have had time to share knowledge or energy. Another one was the flatness problem, which asked why the universe's shape looks so much like a flat surface. The monopole problem asked why we don't find traces of the high-energy particles that should be there if the universe really did start the way we think it did. To solve these, cosmologists proposed a tweak in the 1980s called cosmic inflation. It posited that in the first tiny fraction of a second after the Big Bang, the universe expanded exponentially, faster than the speed of light. This inflation would have smoothed out irregularities, stretched space flat, and diluted unwanted relics. It became an add-on to the standard model, not part of the original Big Bang theory, but now inseparable from it in most modern versions. So today, when scientists say Big Bang, they're usually referring to a composite theory, an initial singularity, followed by rapid inflation, followed by slower expansion, cooling, the formation of hydrogen and helium, the release of the CMB, and finally, the emergence of structure. It's important to note that the Big Bang theory doesn't try to explain why the universe began or what came before. In fact, in the traditional view, time itself began with the Big Bang. There is no before. The theory also doesn't say much about the true nature of the singularity, because at that point, our equations break down. Quantum effects dominate, and general relativity loses its predictive power. This is where the James Webb findings become so unsettling. The theory predicts a slow, gradual emergence of structure from chaos. Galaxies should form over time, stars should evolve through known fusion processes, and everything should align with the timeline set by the cosmic microwave background and redshift measurements. But if Webb is seeing galaxies that are too old, too big, and too organized too soon, then that timeline may be wrong. And if the timeline is wrong, then the basic ideas that redshift, distance, and age are based on might also be wrong. That means the universe's age, or even the rate at which it is expanding, might be wrong. Even worse, what we think we know about space, time, and light might not be full, which would make our whole model of the universe shaky. Strange galaxies in Hubble's deep field. Astronomers have known for a long time that galaxies were acting badly, even before the James Webb Space Telescope sent back its jaw-dropping pictures. The Hubble Deep Field, which is one of the most famous sets of pictures ever taken, gave us the hints. With telescope time, what started out as a risky bet turned into a new way to see into the past. In 1995, astronomers pointed the Hubble Space Telescope at what seemed to be a completely empty patch of sky. No stars, no galaxies, no obvious targets, just darkness. They kept the shutter open for 10 consecutive days. What they found stunned everyone. Thousands of galaxies, densely packed into what appeared to be nothing. Each smudge, each spiral or fuzzy arc was a galaxy, some over 10 billion light-years away, meaning we were seeing them as they existed near the dawn of time. Astronomy was changed by this one picture. It told us that there were a lot more galaxies in the universe than we had thought. Some people thought that by looking deeper into space, we could see earlier and earlier steps of how the universe evolved. This proved that idea. Over the years, Hubble would use this method over and over again, creating the ultra-deep field and the extreme deep field, which got closer and closer to the theoretical limit of what could be seen. But as the resolution improved and the redshift data accumulated, something strange began to emerge. Some of the galaxies in these deep field images appeared too evolved for their apparent age. They had complex structures, spiral arms, bulges, and even signs of rotation. These weren't the chaotic, irregular protogalaxies expected from simulations of the early universe. These looked like mature galaxies, and yet, according to redshift calculations, they existed just a few 100 million years after the Big Bang. At first, these were just thought to be random outliers. It's possible that the galaxies were being mistakenly named. Their light might have been distorted by gravity lensing, or maybe it was just a fluke, a few odd cases that didn't hurt the model as a whole. But the unease didn't go away. A lot of studies came out and they all said the same thing. Galaxies appeared too early, stars had metal contents that were not expected, and black holes were too heavy for their age. Even though the basic model was still the best, it was taking hits. The problem came down to cosmic timelines. According to the Big Bang framework, it should take hundreds of millions of years for gravity to draw together gas into stars, for those stars to live and die, and for their remnants to form more complex systems. Heavy elements, what astronomers call metals, are produced in the cores of stars and scattered by supernovae. So the early universe should have been metal-poor and structurally primitive. But some Hubble Deep Field galaxies defied this expectation. They seemed chemically enriched, tightly bound, and rotationally stable. A case from a galaxy called GNZ11 was one of the most convincing. Hubble saw GNZ11, and spectroscopy later confirmed it. It looked like it existed only 400 million years after the Big Bang. It was as heavy as a billion suns, though, and it showed signs of star formation at a speed that shouldn't have been possible at that point. Not only was it surviving, it was growing. Still, astronomers remained cautious. Hubble's capabilities, while groundbreaking, had their limits. The deeper it looked, the harder it became to resolve faint galaxies from noise. And infrared sensitivity, crucial for detecting very distant redshifted objects, wasn't Hubble's strongest suit. What was needed was a telescope that could look deeper more precisely, and with an eye tuned to the cool, stretched light of the early universe. That telescope would be James Webb. But what's critical to understand is that Webb's most shocking discoveries didn't come out of nowhere. The seeds of the current cosmological crisis were already planted in the deep field images. The signs were there, of galaxies evolving too quickly, stars forming in unexpected environments, and mass accumulation happening faster than any current model predicted. The way science deals with these kinds of contradictions is what makes this change so strong. To begin with, the material is not believed. Then it is looked into, questioned, and often added to ideas that already exist. But at some point, when the strange things start to add up and can't be explained away any longer, science will have to change. What started out as a few strange galaxies in a deep field picture may now be seen as the first cracks in the Big Bang's base. Too many mature galaxies, too soon. Not only did the James Webb Space Telescope take stunning pictures of the universe, it also showed us a huge problem with how we think about cosmic time. It was thought that gravity and atomic chemistry would slowly make galaxies over billions of years. However, they were found to be fully formed, massive, organized, and very old, only a few 100 million years after the so-called Big Bang. It wasn't just one or two either. There were too many. Within weeks of Webb's first deep field observations being released, astronomers began to notice something they hadn't expected: a population of galaxies so large and so developed that they broke the model. Scientists anticipated finding tiny misshapen clouds of gas, small protogalaxies just beginning to coalesce. What they actually saw were massive systems, some with stellar masses equivalent to our Milky Way, already thriving just 300 to 400 million years after the supposed start of the universe. According to standard cosmology, this shouldn't be possible. It takes time for atoms to form after the Big Bang. It takes time for gas clouds to collapse into stars, and more time still for those stars to die, spread heavier elements, and form successive generations. Galaxies are not supposed to appear already formed at the very beginning of time. They're supposed to grow gradually, shaped by mergers, starbursts, and feedback processes over billions of years. But Webb revealed a cosmos that looks more like a cosmic showroom, already polished and assembled far earlier than theory allows. Researchers led by Dr. Ceyhan Kartaltepe did one of the first tests that made people very worried. They looked at the early science data from JWST and found dozens of bright, huge galaxies with redshifts greater than 10. For that amount of time, the universe was younger than 500 million years. Still, these galaxies showed signs of being not only very big, but also chemically rich and fully developed in their shape. They were shaped like rings, bulges, and maybe even twisting arms. They looked like survivors from the past, rather than babies from another world. This wasn't just surprising. It was impossible, according to the math that underpins the Big Bang model. To create galaxies of that size would require either faster than expected star formation, unknown mechanisms of mass accumulation, or a completely different timeline for the early universe. And the numbers didn't add up. The rate at which matter could clump together, form stars, and organize into galactic structures simply couldn't produce the volume of galaxies Webb was detecting. Not that fast. Some tried to explain it away by tweaking star formation models. Maybe these early galaxies were just forming stars more efficiently than we thought. But this explanation hit its own wall. The more efficiently stars form, the more radiation and feedback they emit, which should inhibit further star formation, not accelerate it. Others suggested that the galaxies were being misidentified, or that redshift estimates were off. But the spectroscopic confirmation soon followed, validating that these galaxies really were as old and as massive as they seemed. The huge number of fully grown galaxies really made cosmologists sit up and take notice. There might be something strange about the one or two that were there. But Webb's research showed a group of people, a trend, or a fact of statistics that couldn't be ignored. Not only was the early world more organized than imagined, there were also a lot of big things in it. Was our understanding of cosmic time itself flawed? If galaxies were forming too fast, maybe time in the early universe doesn't behave the way we think. Or maybe redshift doesn't map cleanly to distance and age, at least not in the way our current models assume. If so, then a fundamental pillar of observational cosmology, how we determine the age of distant objects, may need to be revisited. When you think about what this means for cosmic development, the problem gets even worse. What would that mean for our knowledge of structure creation, dark matter dynamics, and feedback processes? if galaxies didn't take billions of years to fully form? What it's like to find skyscrapers in fossils from the Bronze Age? There is a big mistake in the order of things. For decades, the Big Bang Theory has been more than just a scientific model. It's been a creation story, told in equations and light. It promised a narrative, from simplicity to complexity, from hot plasma to humans. But Webb has cast doubt on the pacing of that story. Maybe the script isn't wrong, but the timing is. Or maybe, more radically, the story we've been telling is incomplete, or wrong altogether. And this is just the beginning. The James Webb Space Telescope will be observing these early galaxies in greater detail in the coming years. With better spectroscopy, refined imaging, and deeper surveys, we'll either confirm these anomalies or watch them multiply. Either way, the tension is building. Galaxies that are too big, too old, too fast. Astronomers thought that the early deep-field pictures from the James Webb Space Telescope would show small, jumbled galaxies. These were the rough sketches of what would later grow into beautiful spiral galaxies and huge elliptical galaxies. Instead, they found something that shouldn't have been there. Galaxies that looked like they were already finished, big, old, and moving quickly. These were not random outliers or mistakes. They were all over Webb's view, and they directly contradicted the usual story of how the universe evolved. In our current understanding of the universe, there's a certain pace to how things form. Galaxies begin as small clumps of matter in the early universe, gradually growing over billions of years through mergers, gravitational accumulation, and bursts of star formation. This hierarchical model, small structures merging into larger ones, is deeply woven into Big Bang cosmology. But Webb found galaxies that skipped that process entirely, appearing massive and complex far too early. One galaxy in particular, Sears 1749, was estimated to exist just 500 to 600 million years after the Big Bang. Yet its mass appeared to rival the Milky Way, a system that took over 13 billion years to evolve. How could something so large already exist when, by current models, there simply hadn't been enough time to form that much structure? The data suggested these galaxies weren't just visible, they were thriving. Some were forming stars at rates 10 to 20 times greater than expected. Others showed signs of ordered rotation, with clear galactic disks, a feature that typically requires time, mass, and stability to develop. It wasn't just size that raised eyebrows, it was the age of these galaxies, or at least what they implied about the passage of time in the early universe. If they were indeed fully formed at such high redshifts, it meant their stars must have begun forming even earlier, possibly within the first 100 to 200 million years of cosmic history. That's an incredibly short window for cooling, gas collapse, star formation, and galactic organization. Far shorter than the Big Bang model would typically allow. Another question is velocity, or how fast these galaxies were making stars and adding mass. The rates at which stars were being formed were often so fast that they went beyond what is called the Eddington limit. This is the possible top rate at which matter can fall into a structure without being blown apart by radiation pressure. Not only were these galaxies growing quickly, they were doing so at speeds that push the edges of what is possible in astronomy. Three things, too big, too old, and too fast, combine to make a contradiction. It's not enough to just explain away one strange thing. To get the numbers to line up, you'd have to make a lot of changes to the usual theory. And even then, the stress wouldn't go away completely. The Big Bang model gets stronger with each early huge galaxy that Webb finds. As a way to make sense of the results, scientists suggested that early galaxies might have been more efficient than modern ones, for example by using their gas stores more quickly. But that just puts things off. How could that level of efficiency appear so quickly in such large numbers, and over such large areas of the early universe? Also, why didn't models say it would happen? Another theory suggested that perhaps dark matter clumps in the early universe created deep potential wells, allowing matter to collapse faster than expected. But even this tweak struggles to explain the sheer number of massive galaxies Webb has found, and it doesn't account for the metallicity and organized structure seen in so many of them. If the timeline of galaxy formation is off, it might mean our measurements of distance, based largely on redshift, need to be re-examined. It might also mean that time in the early universe functioned differently than we assume, or that the cosmic expansion model itself needs updating. Perhaps the laws of physics we observe today didn't hold exactly the same way when the universe was young. These questions are now rippling through astrophysics like shockwaves. The standard model of cosmology, known as LCDM, lambda cold dark matter, has long been considered robust. It accounts for expansion, the cosmic microwave background, large-scale structure, and more. But James Webb's findings are testing the edges of that confidence. Some scientists have even called the early results a crisis in cosmology, one that demands either serious revision or radical reinterpretation. Meanwhile, the Webb telescope continues to deliver. Every new image, every deeper exposure, seems to reveal yet another galaxy that's too big, too old, or too fast to fit the timeline. And while researchers are hard at work refining measurements and testing alternatives, the broader picture is hard to ignore. The early universe looks far more like a cosmic metropolis than a construction zone. It's still too soon to say whether these discoveries will overthrow the Big Bang theory entirely. Paradigms don't collapse overnight, but history shows us that when observation contradicts theory, the burden is on the theory to adapt. Redshift reconsidered. One of the most important ideas in astronomy is the idea of redshift. It tells us how far away something is in space. That's how we plot time. And it's the very thing that tells us how far away and how far back in time a galaxy is. But now that James Webb has found new things, some scientists are starting to wonder, did we get redshift wrong? To understand the weight of that question, you first have to understand what redshift is supposed to tell us. When light travels from a distant object through the expanding fabric of space, it stretches. Just like the sound of a receding ambulance lowers in pitch, the wavelength of light increases as its source moves away from us. Blue light becomes redder, hence the term redshift. In cosmology, redshift is also used to track cosmic expansion. The higher the redshift, the farther away the object is, and crucially, the further back in time we're seeing it. An object with a redshift of 2 is being observed as it was when the universe was roughly 3 billion years old. An object at redshift 10, that's from when the universe was less than 500 million years old. The higher the redshift, the closer we are to the Big Bang. We use this relationship to build the entire cosmic timeline, from the formation of stars and galaxies to the appearance of black holes, even to the rate of universal expansion. In essence, redshift isn't just a measurement, it's the backbone of cosmic history. The galaxies observed at extreme redshifts, values of 10, 11, 12 and beyond, aren't behaving as expected. They're too big, too evolved, too structured, as if they've had far more time to grow than the timeline allows. One explanation is that these galaxies are somehow younger than they appear, that their brightness, mass, or structure is misleading. But another, more radical possibility is that our interpretation of redshift is flawed. Could it be that redshift isn't telling us what we think it is? That perhaps cosmic expansion isn't the only or even the correct reason for why light gets stretched over vast distances? This is not a new question. In fact, it's one of the oldest controversies in cosmology. When Edwin Hubble first saw that galaxies were redshifted and looked like they were moving away from us in the early 1900s, some scientists came up with other ideas for why this might be happening. The tired light theory was one of the most famous. It said that photons lose energy by interacting with particles or fields in space, which makes them redder. In that view, redshift would not show that something is expanding, but that photons are getting tired after traveling long distances. That theory fell out of favor for lack of supporting evidence and for failing to match certain observed features of the universe, like the precise spectrum of the cosmic microwave background. Still, Webb's findings are giving new life to old questions. If expansion alone can't explain the strange maturity of high redshift galaxies, Is there something else affecting how we interpret redshift? On a higher level, there are also theoretical theories that question redshift. Some scientists think that space-time might not be smooth, especially in the beginning of the world. Light might have redshifted in ways we don't understand right now if space-time curves or quantum fluctuations were stronger in the past. Others say that light might combine with dark matter or energy in ways that change its frequency over billions of years. Still others point to the possibility that light behaves differently at quantum scales, meaning redshift could be influenced by factors that aren't part of the standard model at all. If space is granular, if time is emergent, or if the speed of light itself has changed over cosmic history, then everything we assume about redshift might be built on a moving foundation. There's also the unsettling realization that much of our redshift calibration depends on models we're now questioning. We use redshift to estimate distance, but we also use models of galaxy evolution to infer redshift. This circular logic becomes dangerous when the very models that interpret redshift are being challenged by the Webb data. It's too early to throw out redshift entirely. The idea remains one of the most predictive and consistent features of cosmology. But the precision with which we equate redshift to time and distance may need recalibration. It might be that redshift does indicate expansion, but not in a linear one-size-fits-all way. Or that in the earliest epochs, something unknown distorted the relationship we've come to trust. The impossible stars. The first generation of stars, the so-called population 3 stars, were supposed to be seen by the James Webb Space Telescope. These stars are big, hot, and mostly made of hydrogen and helium. These were supposed to be the first light sources in the universe. They were supposed to have been born in a world that was clean and free of heavy elements. Instead of finding the long thought to be primordial stars, Webb has found something very different. Stars that shouldn't exist that early and formed in a way that doesn't fit with the normal model of cosmology's timing and chemistry. What Webb found were massive, luminous stars embedded in ancient galaxies, radiating intensely, not just with hydrogen and helium, but with clear signs of metallicity. In astrophysical terms, metals refer to any element heavier than helium: carbon, oxygen, nitrogen, iron, all of which are formed in the hearts of stars and scattered by supernova explosions. The presence of these elements in early stars implies that several generations of stellar birth and death had already occurred. But Webb is seeing these enriched stars just a few 100 million years after the supposed Big Bang. That leaves almost no time for multiple generations of stars to live, die, and recycle their materials into more complex offspring. This shouldn't be happening. Under the Big Bang framework, the first stars form after cosmic recombination, when electrons and protons combine to form neutral atoms, and the universe cooled enough for gas to clump under gravity. These population 3 stars, if they existed, would live short, violent lives, exploding in brilliant supernovae and paving the way for second and third generation stars enriched with heavier elements. But this process takes time, hundreds of millions of years, if not longer, to build up the levels of metallicity we're seeing in stars that appear to exist far too soon. Webb's discovery of stars with high metallicity at such extreme redshifts poses a serious problem. It doesn't just suggest early star formation, it suggests early chemical evolution at a speed and scale that current models can't replicate. In galaxies like GNZ 11 and CRS 1019, stars appear to be not only burning hot, but chemically complex. That complexity requires a stellar life cycle that should be impossible within such a short cosmic window. Some experts have tried to explain this by saying that stars formed very quickly in the early universe. It's possible that the conditions in the very first galaxies made it possible for stars to form, live, and die much more quickly than was thought before. They might have been denser, cooler, or had crashes caused by shock waves that started the chemical cycle right away. But this idea isn't logical, because Webb isn't just finding one richer star or galaxy, it's finding a lot of them. This common trend makes it seem like the early universe wasn't a blank canvas just waiting to be drawn, but a scene that was already full of details. What's even stranger are stars that are too big for existing theories to understand. Based on Webb's findings, Some of the stars may have masses hundreds of times bigger than our Sun, which could be close to the theoretical upper bounds. The usual view is that big stars are unstable, and the radiation pressure should break them apart or make them fall into black holes. But in the early galaxies Webb looked at, huge stars not only seem possible but also common. These impossible stars shine with such luminosity and complexity that it's hard to imagine them forming without some precursor conditions. But there shouldn't have been enough time since the supposed origin of the universe for those conditions to exist. Even accounting for gravitational collapse and rapid cooling, the interval between the Big Bang and the formation of these stars is alarmingly short. What if the universe didn't start with simple hydrogen clouds and a clean slate? What if instead the early universe was already chemically active, already building stars with metals, already forming systems more advanced than we expected? That would suggest a very different origin, or at least a different pacing, than the Big Bang theory allows. Some strange ideas, like plasma cosmology or steady-state models, say that the universe is endless or circular, and that matter and energy are always changing instead of being created in a single event. These points of view say that early stars aren't really early. They're just a part of a process that happens over and over again in the universe. These models haven't been used in a while, but Webb's results are giving them some attention again. There's also the chance that our entire model of stellar evolution is missing something. Perhaps the physics of the early universe allowed for faster fusion, quicker lifespans, or exotic stellar behaviors we don't yet understand. Maybe dark matter played a catalytic role. Maybe there's an unknown factor influencing how stars are born, live, and die. But until those gaps are filled, we're left with a universe that seems to be cheating the rules. The stars that were supposed to be impossible, too massive, too old, too enriched, are not only real but common. And they're rewriting the story of how light returned to the cosmos. Ancient black holes where there should be none. People often think of black holes as the grim reapers of the universe. They are the dense, collapsed remains of very massive stars or the enormous monsters that lurk at the centers of galaxies. Their birth is not simple or quick. Black holes are thought to be the end of time in the standard model of astronomy. To form, live, and die, they need generations of stars. They want mass, mergers, and brutal, slow construction. They are, however, being found everywhere by James Webb way too early and way too big. Supermassive black holes, those with millions or even billions of times the mass of our Sun, are normally associated with well-evolved galaxies. Our own Milky Way hosts one, Sagittarius A star, sitting calmly at the center, a gravitational anchor that formed over billions of years. But Webb's observations are detecting active galactic nuclei, AGN, the bright energetic signals of material spiraling into black holes, in galaxies that exist less than 700 million years after the Big Bang. Some of these black holes already appear to have masses in the hundreds of millions of solar masses, and that timeline is a problem. This is not something that can be done quickly. It takes time. Even if you start with a seed black hole, which would be the remains of a very large population 3 star, maybe 100 solar masses, it would have to keep growing through accretion and collisions with other galaxies in order to become supermassive. It takes hundreds of millions to billions of years for that process to finish, even in the most hopeful models. Webb, on the other hand, sees them fully grown before the universe was formed. This isn't just early black hole formation. This is early black hole domination. Some of the host galaxies appear to be centered around these giants, suggesting that black holes were not just a consequence of galaxy formation. They may have been a prerequisite. That flips the traditional model on its head. Sears 1019 is one of the most shocking examples. It is a live galaxy with a giant black hole that was around when the universe was about 570 million years old. Even more amazing is that it looks like it is accreting matter, which means it wasn't inactive and was actively eating gas and changing its surroundings. This is the kind of behavior that galaxies usually show when they are much further along in their growth. Some scientists have proposed that these black holes formed from direct collapse, an alternative mechanism where massive clouds of gas collapse directly into a black hole without ever becoming a star. This would create larger seed black holes from the start, allowing them to grow more quickly. But even this theory struggles to explain how such seeds could be in place and already accreting so early, especially in galaxies that are also forming stars rapidly. To grow so quickly, these early black holes would need not just mass, but an abundant fuel supply. Cold gas, dust, and matter falling in at just the right rate. But such smooth, rapid feeding contradicts many of our models, which assume turbulence, feedback, and fragmentation would slow the process. And yet, Webb is finding these monsters already formed and active, quietly violating every timeline we thought we understood. Even more concerning is the number of early supermassive black holes. They're not rare gems. They appear to be common features of early galaxies. That implies a universal process, not an exception. And that, in turn, suggests something far deeper might be wrong with our assumptions. If black holes this massive existed so early, it changes how we understand structure formation, star formation, and even reionization, the process by which the first light sources transformed the universe's opaque hydrogen fog into transparency. Black holes, through their energetic radiation, may have played a far larger role in shaping the early cosmos than previously thought. Some people are even starting to think that black holes might not be the end of evolution, but the beginning. Some models now think that primordial black holes, which didn't form from stars, but straight from quantum changes in the very early universe, might have been the first things that led to the formation of galaxies. Black holes didn't wait for galaxies to form around them in this version of events. It was around the black holes that the galaxies formed. It's an unsettling reversal, and it forces cosmologists to confront uncomfortable possibilities. If supermassive black holes are this ancient, this common, and this central to galactic life, then maybe our universe didn't evolve in the slow, linear fashion we imagined. Maybe it sprang into complexity faster than we thought possible, or maybe it always had it. Dark matter in crisis. Dark matter has been the universe's quiet framework for decades. It is the mysterious material that makes up more than 80% of all matter in the universe and holds galaxies together. It does not give off light, reflect light, or interact with the electric force, but its pull on the universe can be felt everywhere. That's what we thought anyway. The James Webb Space Telescope is here. Webb's study of the universe's oldest galaxies and structures has not only raised questions about how old and how big these things are, but it has also started to question the framework that these things are meant to hold together. However, when we use dark matter models on Webb's data, we find something very troubling. The math doesn't add up. The standard cosmological model, known as LCDM, short for lambda cold dark matter, relies on the idea that dark matter clumped together early in the universe, creating gravitational wells into which normal matter could fall. This clumping is what supposedly triggered the formation of galaxies, stars, and eventually planets. Dark matter wasn't just a background player, it was the first actor on the stage. But Webb's observations are now suggesting that large, well-structured galaxies appeared far earlier than LCDM allows. If these galaxies had dark matter halos, which they must according to the model, then those halos would need to form extremely rapidly, more rapidly than the model permits. In other words, if dark matter was doing its job in the early universe, it was doing it too fast. On the other hand, Webb's observations of some galaxies show that they depend less on dark matter than was thought. The spectral data we use to figure out their mass distributions and spin shapes don't always match up with what we would expect from dark matter. These galaxies act like they're held together by less unseen matter than the model says they should be. This isn't the first time dark matter has raised eyebrows. Even in the nearby universe, some galaxies, like NGC 1052 DF2, have appeared to contain virtually no dark matter at all, defying the expectations of galactic formation theory. But these were rare, localized puzzles. What Webb is showing is that the earliest galaxies, supposedly shaped entirely by dark matter, are not behaving as dark matter-dominated systems should. The way the structure is spread out is another point of tension. It takes time for dark matter to gather into clumps in CDM. In the beginning, the universe should have been mostly smooth, with small changes over time turning into strands, nodes, and gaps. But Webb is finding galaxies that are not only closer together, more lined, and sometimes more orderly than theory says they should be. Without highly developed dark matter support, there shouldn't be this much order. But where did the order come from if the dark matter didn't have time to set itself up in those ways? First, perhaps dark matter behaves differently than we thought. Maybe it's not as cold as LCDM suggests. If it's warm or self-interacting, it might clump faster or distribute itself differently. But these modified versions of dark matter create their own problems and don't fully align with other observations, such as those of the cosmic microwave background or galaxy cluster dynamics. Second, it may mean that alternative gravity theories, long considered fringe, need to be re-examined. Models like MOND, Modified Newtonian Dynamics or TVs, attempt to explain galactic rotation and structure without invoking dark matter, instead modifying how gravity works at large scales. These theories have struggled to explain all observations, especially on cosmological scales. But Webb's revelations may provide new ground for hybrid models that blend modified gravity with limited dark matter. Third, and perhaps most radically, it could mean that dark matter as we conceive it simply doesn't exist, or at least not in the form we've theorized for nearly half a century. Maybe our gravitational equations are incomplete. Maybe our understanding of mass and energy in curved space-time is flawed. Or maybe we're missing a layer of physics entirely, one that Webb is beginning to expose not with direct evidence, but through persistent mismatch between prediction and reality. The most important thing about this problem is that dark matter isn't just a placeholder in our models. Modern astronomy, astrophysics, and particle theory are built on top of it. In some ways, it even explains how galaxies form and how the universe is structured. Dark matter is needed for the dominoes to fall if it fails. Dark matter is not being directly found by James Webb. It can't. But by pushing the edges of what can be seen in terms of time and resolution, it is trying what would happen if dark matter existed. And those effects are looking more and more stressed so far. Reconsidering cosmic inflation. For a long time, cosmic inflation has been seen as one of the best ways to explain the universe. It was a bold addition to the Big Bang theory when it was first put forward in the early 1980s. It wasn't part of the original framework, but it was needed to fill in some of its biggest gaps. The main idea behind inflation is that the universe grew very quickly and exponentially just a few fractions of a second after the Big Bang. Space grew bigger than the speed of light for a very short but important moment, stretching the universe flat, smooth, and even. Inflation was introduced to solve problems. The horizon problem, for example. Why does the universe look the same in every direction, even though distant regions shouldn't have had time to exchange light or information? Inflation says, because those regions used to be in contact, until inflation blew them apart. Then there's the flatness problem. The universe appears to be geometrically flat, which should be extremely unlikely. Inflation says, that's what happens when you inflate a small curved patch of space. It flattens out. Neat, clean, mathematically clever. But there's one thing inflation didn't do. It didn't make any direct testable predictions when it was first proposed. It was speculative, and for years it remained on shaky ground. Later refinements gave it more mathematical rigor, and its predictions, especially about the spectrum of cosmic microwave background fluctuations, lined up remarkably well with observations. That cemented inflation's role in the cosmological mainstream. It became standard doctrine. However, inflation has always had a strange air of creativity about it, a fix on top of a workaround. With the help of early data from James Webb, the questions that inflation was meant to hide are now coming up again. Webb isn't looking at inflation straight on. That event would have happened about 10:36:10 minus 36, 10:36 seconds after the Big Bang, which is so early that not even light had come into being yet. But Webb is looking at the shape of the universe in its early stages, which is a result of that time of inflation. We notice that the building looks too well put together, too perfect, and sometimes too old the more we see of it. The galaxies that Webb is detecting aren't just forming earlier than expected. They seem to appear fully formed, with large masses and ordered spins, as if they didn't evolve through chaos at all. This is problematic because inflation was designed to explain structure by introducing small quantum fluctuations into a smooth early universe. These fluctuations then seeded the growth of galaxies, stars, and clusters. But what happens when that structure appears almost instantly, without enough time for fluctuations to evolve? The paradox is reversed. Inflation was meant to introduce just the right amount of irregularity into a very smooth universe. But Webb's early galaxies seem to skip the irregularity entirely. They suggest a universe that went straight from inflation, or something like it, into complexity. That either means inflation operated very differently than we thought, or it didn't happen at all. Inflation predicts a very specific spectrum of fluctuation, with certain sizes of structure being more common than others. Yet the cosmic web, even at early times, seems to exhibit a puzzling uniformity, one that doesn't align neatly with inflation's output. If that trend holds, it could indicate a deeper inconsistency between the predictions of inflation and the universe's observed evolution. On top of that, there are philosophical problems. Even though inflation is useful from a mathematical point of view, it has worrying effects. A lot of the time, this leads to the idea of a multiverse, which means that inflation didn't happen just once, but keeps happening forever in some places, creating an infinite number of tiny worlds. By definition, these worlds can't be seen. That means the theory is very hard to disprove and very close to philosophy, which is a very bad thing. Webb's findings bring us back to a crucial question. Did the universe really need a brief moment of unthinkable expansion to explain its current state? Or were we using inflation to cover for gaps in a model that never worked as smoothly as we believed? Some researchers are beginning to revisit older ideas, like bouncing or cyclic cosmologies, where the universe didn't start from a singularity at all, but from the collapse of a prior universe. Others are exploring quantum gravity frameworks, where space and time are emergent phenomena, and the need for inflation disappears entirely. The too smooth universe problem. People often think of the early universe as a sea of high-energy particles, turbulence, and chaos. The universe was meant to slowly change from this fiery start, creating dense areas that would give rise to galaxies and groups. With cosmic inflation added to the Big Bang model, it was thought that the early universe would be mostly smooth, but with some small flaws caused by quantum ripples that were stretched into small changes in density. These tiny variations were critical. They were supposed to be the imperfections that allowed structure to form. A completely smooth universe, after all, would remain smooth. Galaxies need gravitational irregularities, bumps and clumps of matter, to pull together gas and stars. Without these flaws, there's nothing to assemble into stars, planets, or us. In fact, these imperfections are visible in the cosmic microwave background, CMB, showing up as faint temperature fluctuations, the fingerprints of those early seeds. The CMB shows those tiny changes as expected, but James Webb's pictures of the early universe don't seem to show the chaos that those seeds should have caused. Webb is looking at a universe that is too smooth, too symmetrical, and too calm to find signs of a universe that is still putting together its structure. This isn't the ease that comes from being the same everywhere. It's not that galaxies are spread out evenly. They're showing up in places, numbers, and shapes that are hard to predict. It's more that the rate and organization of structure creation look too clean and advanced for how soon after the Big Bang they're happening. Galaxies are showing up with spins that are in order. Clusters are coming together in a very consistent way. Things aren't as messy as they should be, which is disturbing. According to the inflationary model, the fluctuations should have produced clumpy distributions in the early stages of the universe, regions of higher and lower density, gradually collapsing into increasingly complex arrangements. Webb, however, is detecting galaxies that seem to have bypassed the chaos. In some fields of view, there's a surprising uniformity in size and shape. Structures that should have formed over billions of years seem to be already in place just a few 100 million years after the Big Bang. This problem is similar to what some scientists have said about inflation, that it fixed too many problems that were present in the world at the start. Inflation may have made the universe too smooth by stretching space so quickly and efficiently, leaving not enough room for structure to grow in the way we see it. The galaxies we see with Webb shouldn't exist if that's the case. Still, there they are. Some have proposed that our understanding of early gravitational collapse might be flawed. Perhaps gas and dark matter coalesced faster than expected. But this too has limits. Gravitational systems need time to grow. Even if you crank up star formation efficiency or hypothesize unusually cold dark matter, it doesn't easily account for the scale of the structure being observed. Others point to the possibility that our cosmological simulations, used to predict how structure should have formed, may be oversimplified. Perhaps the universe doesn't evolve the way we've been programming our models. But if that's true, it calls into question the reliability of decades of predictions built on those models, including the very shape of the early universe. There's also the potential that the smoothness is an illusion, that we're seeing galaxies that formed unusually early due to unknown physics, while the rest of the universe lagged behind. But the more Webb surveys the early cosmos, the harder this is to sustain. The anomalies are becoming too common to be rare flukes. Another cosmic puzzle that is related to the too smooth problem is, why is the structure of the universe on a big scale so perfectly balanced? How is it that the rate of growth, the spread of matter, and the curvature are all so perfectly lined up for galaxies to form in the first place? Scientists thought that inflation would explain this, but Webb's results show that the accuracy might be even higher than inflation suggests. It's almost like the world knew exactly what it was doing. What if the early universe wasn't a mess that eventually birthed order, but something closer to a ready-made system? A cosmos that didn't build complexity, but began with it already encoded. That would require a reimagining not just of structure formation, but of the universe's initial conditions, or the absence of a singular beginning altogether. James Webb and the impossible early galaxy problem. It was only a matter of time before someone said they were impossible. This can't be meant in a poetic or figurative way. It's just not possible according to normal physics. The James Webb Space Telescope's first deep field pictures showed these galaxies that don't look like they should. They are too big, too bright, too old, and, most unsettlingly, there are too many of them for any place on the Big Bang timeframe to fit. Astronomers expected Webb to find primitive objects, small, chaotic, gas-rich clouds in the process of becoming galaxies. They expected to see the messy beginnings of order, stars just igniting, and structures forming slowly over hundreds of millions of years. What they found instead were fully formed galaxies shining at redshifts of 10, 12, and even higher, galaxies that existed when the universe was just a few 100 million years old. These galaxies weren't merely surprising because they were there. They were impossible because of how much they had already accomplished. Some contain as many stars as the Milky Way. Others have well-defined disks, stable rotations, and chemical enrichments that suggest they had already undergone several generations of stellar evolution. They didn't look like babies. They looked like adults living in a toddler universe. Webb saw a galaxy called Sears 93316 that has a redshift of about 16.7, which means we are seeing it as it was only 240 million years after the Big Bang. This is one of the most striking cases. Models that are already out there say that this galaxy shouldn't have had enough time to make even its first set of stars, let alone grow up. Still, there it is, clear, organized, and shiny. The reason these galaxies are labeled impossible isn't just because they're early. It's because the timeline for how long it takes to form stars, build mass, and organize into complex structures is grounded in well-understood physics. Gas clouds take time to cool and collapse. Star formation requires density thresholds and gravitational instabilities. Metal enrichment requires the birth and death of multiple generations of stars. These are not processes that can be rushed. And yet, somehow, these galaxies seem to have done it all within the first 2% of the universe's lifespan. When Webb began returning its early data, many assumed that some of these galaxies were being misidentified, that their redshifts might be overestimated due to photometric confusion or contamination by nearby objects. But as the spectroscopic confirmations began rolling in, the reality set in. These redshifts were real, and so were the galaxies. This has led to a growing chorus within the astrophysics community. Something about our model is broken. Some theorists have proposed revising star formation rates, assuming these early galaxies were much more efficient at converting gas into stars than modern ones. Others suggest a new class of ultra-dark halos that might have accelerated collapse. But these patches only go so far, and they raise new problems. If star formation was that efficient, why don't we see similar behaviors in more recent cosmic history? If mass collapsed that quickly, what does that say about the nature of dark matter or the influence of unknown forces? And perhaps most fundamentally, why didn't our models predict this? That's the question that keeps resurfacing. For decades, cosmological simulations have guided our expectations for what the early universe should look like. We built a framework, the LCDM model, that told us when galaxies should form, how large they should be, and how they should evolve. But Webb has pulled back the curtain and revealed a stage already full of players before the play was supposed to begin. It's not just that these worlds are there that makes people feel uneasy. It means that our whole idea of how the universe is put together may be wrong in terms of time. What else did we get wrong about the early universe if it wasn't a slow build-up of complexity, but a quick jump into it? Today, the impossible early galaxy problem is one of the most important and hotly discussed mysteries in the field of astronomy. Plus, there's more than one note. There is a threat to the timeline itself, and we need to either completely change our ideas or come up with a new model. No time for evolution. Why the early universe looks ready-made. Modern astronomy is based on the idea that things get more complicated over time. Galaxies don't just appear like light bulbs turning on, they change over time. They begin as clouds of hydrogen and helium, stick together because of gravity, give birth to their first stars, get more material through the death of stars, and slowly change into the moving structures we see today. It is thought that this process of the universe growing up from simple to complex will take billions of years. But the James Webb Space Telescope has a different view, one in which the early universe didn't change slowly over time. It came into being fully formed. In every deep field image, James Webb is finding galaxies that look complete, not on their way to becoming something, not assembling, already there, with star formation rates that rival modern galaxies, with disks, bulges, and spiral arms, with chemical signatures that suggest multiple generations of stellar recycling. These aren't rough drafts, they're polished chapters, appearing just a few 100 million years after the supposed Big Bang. According to our models, the cosmic dark ages, the period between the release of the cosmic microwave background and the first stars, should have lasted around 200 to 300 million years. During this time, the universe was cooling, and gravity was slowly beginning to work on the first neutral atoms. After this phase, the earliest stars and galaxies were expected to begin forming, messy, metal-poor, and small. But what Webb is showing instead is a universe that seems to have skipped the awkward adolescence altogether. Some of these galaxies have stellar masses comparable to the Milky Way. That means they would have needed to form stars at breakneck speed, turning gas into suns with an efficiency that no current model supports. Even the most aggressive starburst scenarios, events that trigger rapid star formation, can't explain how galaxies this big could exist this early. If galaxies formed so quickly and completely, it means our timeline for cosmic evolution is wrong, possibly by orders of magnitude. It raises the uncomfortable possibility that the universe wasn't a slow, unfolding narrative, but something preloaded with structure, just waiting to be observed. What does it mean if the universe didn't evolve, but began already evolving? The entire appeal of the Big Bang model has been its explanatory power, a way to tell the story of how simplicity becomes complexity. But if complexity was there from the beginning, the story changes. Instead of emergence, we're looking at something closer to appearance. This doesn't have to mean magic or design, but those are the kinds of thoughts that come up when science runs into a problem. It could just mean that we don't know enough about how the world started. It's possible that things were very different in the early universe than we think. The physics of structure creation may have been based on rules or laws that don't hold anymore. Or maybe, just maybe, time doesn't work the way we thought it did in the beginning of time. It's also possible that the time in space is wrong. If redshift isn't a great way to tell how old something is, and if distances and timescales are off, then these galaxies might not be as old as they seem. It gives us some time, but only for a short time. Even the most generous recalculations can't make a few 100 million years into the billions of years that are needed for evolution to make sense. What's more, the uniformity of these early galaxies adds to the puzzle. If the early universe had pockets of premature complexity, that would be strange enough. But what Webb is finding appears to be a consistent pattern. Not one or two galaxies that broke the rules, but entire populations of them. That consistency suggests this wasn't a fluke. It was the norm. Some cosmologists are starting to say that the early universe is like a stage that's already set. When the lights come on, the players are already dressed and say their lines. They don't practice or get ready for it. There is only a universe that is ready to go, organized and working. That image is difficult to reconcile with a model built on gradualism. And it means that whatever is going on in the early universe, it's faster, more efficient, and more organized than anything the standard model accounts for. Cosmic dawn, or was it cosmic noon? For decades, scientists have been waiting for the day we could see the cosmic dawn. This is the moment when the first stars came into being, ending the Dark Ages and lighting up the world. At that time, the universe was supposed to be very quiet and uncertain. Stars would be spread across the cosmos, sparking in a sea of neutral hydrogen to make the first galaxies. As it slowly went from nothing to light, it was to be our view of the beginning of form. But with the arrival of James Webb's early data, a haunting possibility is now emerging. What if the universe's dawn was already halfway through the day? What if what we thought was the gentle sunrise of creation was, in fact, the midday of a cosmic cycle? Bright, busy, and far more advanced than any origin story suggested. The term cosmic dawn implies a beginning, the first light, the tentative start of evolution. But the galaxies Webb is seeing at redshifts of 10, 12, even 16 are not hesitant or dim. They're luminous, structured, dynamic. They're forming stars at rates comparable to modern galaxies. Some are even outshining galaxies that exist billions of years later. This is not a flicker in the void, it's a blaze. This change is more than just beautiful. It goes against everything we know about the history of the universe. We thought the universe would start up slowly, getting more complicated over time, after generation after generation. Webb instead shows us a universe that seems to have skipped the beginning and gone straight to the end. The early galaxies are bright, but that's not all. They are too bright, too fast, and too in sync with each other. They show up all over the sky, not as oddballs, but as a cohesive group. They have advanced features like disks, metal content, and organized motion that need more time, recycle, and growth than the Big Bang timeline allowed. The effects are huge if this really is cosmic noon. It makes us think that the thing we've been calling the early universe might not be early at all. at least not in the way we believe it is. Before the Big Bang, the universe may have already been well into a previous stage of evolution. It's also possible that the birth of light wasn't a starting, but a return, a reset, or a re-illumination. Some theoretical frameworks, including cyclic or bouncing universe models, posit that our universe is just one phase in an eternal sequence of expansions and contractions. In those models, the Big Bang is not a beginning, but a transition, like the chime of a clock marking the start of a new hour, not the start of time itself. Webb may be giving observational weight to those ideas, because if galaxies are already thriving at redshifts above 12, then what preceded them? What seeded them with structure? What conditions allowed such rapid star formation and complex organization? Entropy is another thing to think about. According to standard thermodynamics, entropy rises over time, which means that chaos builds up. If the universe is hot, thick, and smooth at the start, it should get less ordered over time. But Webb shows us early organization that is not disorganized, but very well put together. That order points to either a low entropy state we haven't thought of yet, or a memory of an earlier cycle that is part of this one. Some scientists are even starting to think that maybe what we're seeing isn't just early light, but inherited light, which means that the structure and organization we see now come from a time before the Big Bang. In this view, cosmic dawn is not the first breath of the world. It was the moment the curtain came down after a break. This is still just a guess, though. Webb's research is new, and ideas about what it means are changing. But it's hard to miss the trend. There are too many bright galaxies, and too many different types of galaxies for a slow, patient dawn to fit. They look more like the start of a universe that is already wide awake and well into its life. The question of not only when the world began, but also how beginnings work, has to be rethought. If the beginning that we thought was the middle turns out to be the beginning, then either time is lying or we're reading the wrong chapter. Revisiting the steady-state theory. There was another theory that explained the beginning of the world before the Big Bang. It was very different from the current theory. Hermann Bondi, Thomas Gold, and Fred Hoyle came up with the steady-state theory in the late 1940s. It described a world that had no beginning and no end. Yes, in their model the universe was growing, but as it did, new matter was always being made to keep the density fixed. Lack of a big flash of start. No single point. There was only one universe that looked pretty much the same everywhere and at all times. For decades, the steady-state theory was a serious rival to the Big Bang. It appealed to the philosophical desire for a universe that was eternal, unchanging on the largest scales, and free from the messy idea of a beginning. But in the 1960s, a death knell sounded. The discovery of the cosmic microwave background radiation, CMB, a faint uniform glow of leftover heat, which the Big Bang predicted and steady state could not easily explain. From that point on, the Big Bang reigned supreme, and steady state was cast aside as a relic of outdated thinking. Until now. Because the James Webb Space Telescope is making some people quietly reconsider. It's not that Webb is disproving the Big Bang outright, but it's revealing cracks, galaxies forming too early, stars with impossible metallicity, black holes that shouldn't exist for billions of years, a universe that looks not young and clumpy, but old and organized, far earlier than the standard model allows. These observations are eerily more in line with a universe that's been ticking along for a very, very long time, not one that started from scratch just 13.8 billion years ago. The steady-state theory doesn't explain everything Webb sees, but it does give us a better way to think about timeless organization. For now, there's no need to hurry the formation of galaxies in steady state. You don't have to say how black holes got so big so fast. If the world has always been there, then complexity doesn't need to appear out of nowhere. It can happen slowly, forever, across time, with no beginning or end. Steady state does still have some issues, though. The CMB is still there, and it's still hard to explain how it fits with the idea that matter is being made all the time. But some cosmologists are starting to wonder, What if we combine the best parts of the two models? What if the early universe didn't start with a single bang, but instead came from a cycle that came before? What if the thing we're calling early is actually late in a bigger story? There are modern variants of steady state that build on this idea. Quasi-steady state cosmology, QSSC, proposed by Hoyle and others later in life, introduced the idea of periodic mini-bangs, local creation events scattered throughout an eternal framework. And now, in the age of Webb, this concept doesn't seem so far-fetched. The galaxies we see at high redshift don't look like the first galaxies. They look like the latest in a long lineage. Galaxies that could have emerged from cosmic conditions already enriched by time. Webb has also complicated our assumptions about cosmic expansion. If expansion doesn't follow the clean exponential path we once believed, if it's influenced by unknown physics, phantom energy, or quantum effects, then the entire clockwork of Big Bang timing may be miscalibrated. A slower expanding universe, or one that expands cyclically, would provide more time for early structures to form, again favoring the long-haul realism of steady-state ideas. It's important to keep in mind that not many cosmologists want to go back to the original steady-state theory. On the other hand, they are starting to dust it off and look at its topics again with new information. Because it's only normal to look at the other options again when the current model starts to show signs of stress, when it has to explain more and more while having less and less prediction power. Plasma cosmology. Was the universe born from energy, not a bang? In the background of standard cosmology, there has been a controversial but consistent alternative that questions not only when the universe began, but also how it did it. This idea, which is called plasma cosmology, doesn't start with a bang. The power is the first step. Plasma cosmology suggests that the universe is not primarily shaped by gravity alone, but by plasma, the fourth state of matter, and the electromagnetic forces that govern its behavior. Developed in part by Nobel Prize-winning physicist Hannes Alfvén, this model proposes that the cosmos is an eternal interplay of charged particles, vast electric currents, and cosmic-scale magnetic fields. Where the Big Bang offers a hot, dense, explosive birth, plasma cosmology sees no beginning, just continuous energy exchange in an infinite universe powered by electrical forces. In a plasma-dominated cosmos, matter doesn't condense solely under gravity's pull. Instead, charged particles respond to electromagnetic fields, which are 10 trillion times stronger than gravity. These fields can channel, shape, and organize matter into filaments, voids, and spirals, patterns we actually see when we map the large-scale structure of the universe. That cosmic web of galaxies and clusters, rather than being a relic of gravitational clumping from a primordial soup, might instead be the product of vast electric currents forming plasma filaments across space. Plasma cosmology has been brushed off as crazy for decades. The cosmic microwave background is hard to explain, and it can't predict the link between redshift and distance like the Big Bang can. But the new results from James Webb are making cosmologists look again. This is because the galaxies Webb is seeing are too young, too organized, and too huge to fit the time frame of a universe that only has gravity. But they might make more sense in one where plasma rules. Stars and galaxies could form much more quickly in a liquid universe. Instead of gas clouds slowly falling apart because of gravity, plasma currents could quickly pull matter into strands and use magnetic fields to pinch them together. This is known as the Bennett pinch. These electromagnetic interactions could cause strong bursts of star formation, which would quickly replenish elements and build structures on a galaxy scale. Sense a pattern? It's no coincidence that plasma cosmology predicted some of the things Webb is just now discovering, not because it's magical, but because its mechanisms allow for speed and structure without the long timelines required by gravitational collapse. And since plasma dominates 99% of the visible matter in the universe, from stars to nebulae to intergalactic space, the theory insists we've been ignoring the true engine of cosmic architecture. The early galaxies Webb has revealed are not just early, they're electrifyingly complex. Some are arranged in filamentary structures, already lined up into what look like embryonic versions of the cosmic web. That kind of order, that kind of large-scale connectivity, shouldn't exist so soon if gravity alone was doing the heavy lifting. But in plasma cosmology, it's exactly what you'd expect from a network of charged matter governed by electric currents on galactic and intergalactic scales. Why not talk about redshift? Plasma cosmology also gives a different reason for this. Instead of just being caused by space stretching, cosmic expansion, this model suggests that redshift could be caused by photons reacting with intergalactic plasma, which makes them lose energy as they journey long distances through an electrically active medium. This would change the way we measure time and space in the universe, which could mean that those old galaxies aren't as far away or as early as we think. To be clear, plasma cosmology is still a very touchy subject. There isn't as much agreement on this model as there is on the Big Bang model. It doesn't have a good theory for the CMB, and it's been hard for it to make forecasts that match what we can see now. There are now cosmologists who are brave enough to ask, was it a mistake to ignore the plasma? Webb is destroying model after model. There's also a cultural angle to all this. Plasma cosmology was never given the spotlight. It rose briefly in the mid-20th century, then fell out of favor. Not because it was disproven, but because the Big Bang had momentum, institutional support, and the mathematical elegance of inflation and general relativity behind it. Plasma cosmology didn't have elegant math. It had dirty, dynamic real-world physics, chaotic, non-linear, and hard to model. But maybe the universe is like that too. James Webb is peeling back a layer of the cosmos we've never seen, and what it's showing us may not be the aftermath of a bang, but the patterns of a living electric cosmos, structured by forces more immediate than ancient explosions. Big Bang versus Big Bounce, a universe without a beginning. The Big Bang has been the standard story about how everything began for almost 100 years. It describes a single point from which all space, time, and matter exploded into existence in an unthinkable way. It is thought that time started about 13.8 billion years ago, and the world has been growing and shrinking ever since. But what if that story isn't whole? What if the world has been moving around for all time and didn't start? Welcome to the world of the Big Bounce, a radical alternative to the Big Bang that suggests our universe is simply the latest iteration in a cosmic cycle of expansions and contractions, an eternal heartbeat echoing across time. It's not a singular explosion, but an ongoing rhythm, the universe collapsing in on itself before rebounding into a new expansion phase. And now, as James Webb peeks deeper into the cosmic past, some scientists are starting to wonder if the evidence aligns better with a loop than with a line. The idea of a singularity, a place with endless density and temperature where the rules of physics don't apply, is at the heart of the Big Bounce. This mathematics oddity, a time when all of our equations don't work, is key to the Big Bang idea. But the Big Bounce gets rid of the singularity for good. From this point of view, the world never really ends. Instead, it shrinks to a very small size and then expands again because of quantum effects, pressure from strange matter, or unknown physics connected to gravity at very small scales. Why revisit this idea now? Because James Webb's discoveries are unsettling the linear timeline. The presence of massive, structured galaxies too soon after the supposed beginning of time, galaxies that seem to skip the early phases of evolution, hints at a pre-existing order, perhaps even the lingering memory of a prior universe. When the universe is moving back and forth, each cycle leaves behind patterns and information that affect the next phase. That might be why galaxies from the beginning look so far along. They're not strange things. They're inheritances, complexities from a previous world that fell, reset, and planted seeds in the one we live in now. It's not just thinking either. The Big Bounce isn't just a guess. A quantum bounce is used instead of the Big Bang singularity in quantum gravity models, especially those that come from loop quantum cosmology, LQC. According to these models, when space gets too dense, quantum effects start to push against it, which stops the collapse and starts a new phase of growth. Time changes, not ends. There's even observational motivation. The smoothness and structure of the cosmic microwave background, and the early appearance of galaxies seen by Webb can be interpreted as signs of a pre-existing order. If the universe is older than we think, not 13.8 billion years old, but eternally old, then there's no need to explain how complexity arose so quickly. It didn't. It's been here before. In a one-shot universe, entropy increases until everything fades into a cold, uniform death. But in a bouncing cosmos, entropy might be reset or recycled with each bounce. Or perhaps the bounce happens in a way that preserves structure across cycles, allowing galaxies and even black holes to leave imprints on the next iteration. Of course, there are problems to solve. One big problem is thermodynamics. How does a world that bounces around keep chaos from building up forever? Every cycle would be messier than the last, right? Some models say that each bounce makes the world a little bigger, which spreads chaos. Others use made-up processes of dumping entropy into other dimensions or branes, which are based on ideas from string theory. Another question is, can we show it? To find traces of a previous universe, we would have to look for marks in our own universe, like imprints in the microwave background, strange anisotropies, or gravity waves that are still present. Some cosmologists think that these clues may already be out there, but they may be hiding in the data and being mistaken for noise or other things that shouldn't be there. The growing popularity of the tired light hypothesis. Redshift has been used to measure the distance between galaxies for a very long time. The farther away a galaxy is, and the longer ago it must have given off that light, the more its light is stretched toward the red end of the spectrum. Modern astronomy is based on this idea so much that it's taken as gospel. Redshift means growth. Also growth? That proves the Big Bang. But what if it doesn't? There is an alternative, an old one, long dismissed, yet now seeing a quiet resurgence in light of James Webb's revelations. It's called the tired light hypothesis, and it offers a very different explanation. That light doesn't redshift because the universe is expanding, but because it loses energy over time as it travels across vast cosmic distances. In this view, photons, the particles of light, gradually tire as they interact with the medium of space. This loss of energy shifts their wavelength toward the red end of the spectrum, just as if they were receding. But there's no actual motion involved, no expansion, no stretching of space, just light running down like a battery as it treks through an ancient, endless cosmos. Fritz Zwicky came up with this idea in the 1920s. It was very different from the thought of the world expanding, but as the Big Bang became more well-known, tired light became less well-known. It was criticized because it didn't explain some data, like how the light curves of faraway supernovas stretch over time, and because it didn't give a specific physical explanation for how light loses energy without spreading out or becoming blurry. Still, it never fully vanished. And now, with James Webb showing us galaxies that seem too mature for their redshift, the tired light model is gaining quiet attention once again. Because if those galaxies aren't as far away, or as early, as redshift implies, then the entire timeline of the universe collapses inward and many of the Big Bang's deepest mysteries dissolve. In a theory called tired light, those early big galaxies that Webb saw might not have been so early after all. Their redshift is still high, but it's not a timestamp. Instead, it's a product of distance that shows how much energy their photons have lost. It would mean that the world isn't moving away from itself, but is instead staying put, or even infinite and endless. Galaxies aren't shooting outward from a single point of start. They're just there, spread out in space-time, and their light ages as it reaches us. Some of the problems Webb has caused can be solved in a beautiful way from this point of view. They have plenty of time, so the galaxies aren't growing too quickly. The black holes aren't too early. They're very old, and their growth has been slow and steady. Stars' metal content doesn't go against the rules for how galaxies form. It shows that the universe has been around forever. Tired light is still being criticized. One big problem is that there is no picture fuzz. If interactions were making photons lose energy, wouldn't they spread, making galaxies far away look fuzzy? But new versions of the theory suggest more delicate ways that it doesn't work. These could be quantum-level energy leaks or interactions with an unknown feature of the vacuum. There is also the cosmic radio noise to deal with. According to the theory of the Big Bang, it is radiation left over from a hot, dense early state. Tired light doesn't have a straight replacement yet. Some supporters say that what we think of as the CMB could be looked at again through a different lens, as steady radiation in a universe that will never end, or as the result of emissions from faraway galaxies that spread out over time. These are still just guesses, but they're not seen as crazy anymore. What makes tired light newly relevant is Webb's precision. We're now seeing distant galaxies in greater detail than ever before, and their apparent maturity is hard to reconcile with the standard expansion-driven timeline. If the foundation of that timeline, redshift equals distance, is flawed, then so is our entire cosmological chronology. The re-emergence of the tired light idea is not about nostalgia or contrarianism. It's about asking whether we've mistaken a measurement for a meaning. Redshift may be telling us something, but what exactly is still an open question. James Webb is not trying to prove or disprove tired light, but its observations, galaxies too evolved, structures too organized, timelines too compressed, are giving new breath to old doubts. Doubts that suggest our interpretation of light across space may be more human than universal. How James Webb challenges cosmic microwave background interpretations. The cosmic microwave background, CMB, has been praised as the best proof of the Big Bang for many years. It is the oldest light we can see. It comes from the time when the world was cool enough for atoms to form, which let photons move easily through space. The CMB's steady glow was first seen in 1965. It's often called the afterglow of creation, or the picture of the universe as a baby, frozen in time 380,000 years after the Big Bang. But what if we've been reading that picture all wrong? James Webb Space Telescope, designed not to look at the CMB directly, it's tuned for infrared, not microwave wavelengths, but to observe what came after. By peering into the epoch of the first stars and galaxies, Webb is essentially bridging the observational gap between the CMB and the modern universe. And that bridge is beginning to crack. The problem is this. The CMB says that framework will change in a very specific way. Satellites like COBE, WMAP, and Planck have mapped out very small changes in its temperature. These changes are thought to be the quantum seeds from which all of the structure in the universe grew. We learned how much matter there was, how clumpy the early universe was, and what kinds of structures we could expect to see at different times from the CMB patterns. But James Webb is finding more structure, more complexity, and more huge objects earlier than the theories based on the CMB said they would. That's a bad sign. The CMB is the real picture of the initial condition. Then how did the universe form so quickly and so neatly? Either we don't fully understand how matter formed from the CMB, or the CMB itself doesn't tell the whole story. One major issue lies in the scale of the fluctuations. The CMB reveals temperature variations of only 1 part in 100,000, incredibly smooth. This smoothness has always been a bit puzzling, because such a uniform distribution of matter should take a very long time to evolve into the lumpy universe of stars, galaxies, and filaments we see today. That's why the theory of cosmic inflation was introduced, to stretch and smooth the early universe in a way that preserved just enough imbalance to allow structure to form. But Webb's early galaxy finds look too lumpy and too early. It's like the seeds of structure were bigger or grew faster than the CMB says. This could mean one of two things. Either the structure changed without being affected by the initial changes in the CMB, or the conditions we thought were present at the start were not really there. Another trouble is that everything is the same. The CMB is very isotropic, which means it is the same in all directions. But Webb has found parts of the sky with too many early galaxies. This could mean that the CMB missed some local differences, or that the idea that the universe is the same everywhere on a big scale is wrong. If the early universe wasn't as smooth as the CMB suggests, then either something happened between the CMB and the first galaxies, or the CMB isn't correctly displaying the past. A more serious worry is that we might not understand the CMB at all. There are other models that say the microwave background might not be a leftover from the hot Big Bang, but rather the result of things that happened over a much longer period of time. In some models of quasi-steady state and plasma cosmology, the CMB is not seen as the glow from the beginning of time, but as an equilibrium background radiation. This is made up of emissions from stars, galaxies and black holes that have been spread out and redshifted over eons. There are problems even in the Big Bang model. The Hubble tension is the difference between how fast the universe is expanding as measured by the CMB and how fast it is expanding as measured by nearby galaxies. It hasn't gone away, even though Webb data is making the local rate more precise. There is a problem with our early universe predictions, which come from CMB physics. This says that either the structure of space and time is more complicated than we thought. The James Webb Telescope wasn't built to measure the CMB, but by seeing how the universe actually evolved from that supposed starting point, it's becoming a mirror, one that reflects not just the CMB's predictions, but its possible shortcomings. Early galaxy metallicity, stars that shouldn't be. In the big picture of how the universe evolved, the first stars should have been pretty easy. These so-called population 3 stars were thought to be big, short-lived, and most importantly, metal-free. They were thought to have been formed from primordial hydrogen and helium. When talking about astronomy, metals are any elements heavier than helium. These elements are only possible because stars make them through fusion and supernova blasts. Metals hadn't been around yet, so it makes sense that the first stars couldn't have had them. If you look at this chart, metals are like marks of time. As Webb looks deeper into the early universe, it has found galaxies with metal contents that are much higher than predicted. Some of these galaxies have metal contents that are the same as or higher than our own Milky Way. They're also not very old. They show up at redshifts above 10, which means they were around when the universe was only a few 100 million years old. Multiple generations of stars should not have been able to live and die and spread metals throughout the universe in that time frame. Still, here they are, chemical fingerprints that don't belong in this time period. It's not just a small surprise. It goes against the usual way of thinking about how stars and galaxies evolve. Whatever we thought we knew, those times in the universe didn't even have metals to work with. People thought that the first stars would burn very quickly and very hotly, then burst and make the first iron, carbon, oxygen, and other things. We won't see stars and galaxies with a lot of metal until this process of stellar life-death metal seeding has happened several times. But Webb has found these metal-rich galaxies not only early, but also widespread, not isolated anomalies, but entire populations with high levels of chemical complexity. The problem isn't just the presence of metals, it's the implication that stellar evolution was somehow accelerated, or that it didn't happen the way we thought it did. If the first stars were big enough, they might have lived and died even faster than expected, making their surroundings better in just tens of millions of years. But this situation needs a lot of efficiency. Supermassive stars forming right after the Big Bang, exploding in waves that are timed to each other and starting new waves of star formation right away. It's not impossible, but it sounds like the choreography isn't making sense. There is also a chance that metals were made before the Big Bang, either in a time before the Big Bang or as a bounce from an earlier world. In this light, the world we see is not the first step in the growth of the universe. It is a continuation. Webb's finding of early metallicity isn't proof of faster growth, it's proof of transmission. This idea is especially provocative in light of alternative cosmologies like cyclic models or the Big Bounce. In those scenarios, metals and structures can survive collapse and be reborn into the next expansion. Suddenly, ancient metal-rich galaxies don't look premature. They look like veterans of a previous reality. Another scary question that comes up is whether or not population 3 stars are real. Even though people have been looking for decades, no metal-free stars have ever been seen. Not at all. There is some metal in every star we've seen, even those in the farthest worlds. There may not have been any population 3 stars, or they may have been so rare and short-lived that they didn't leave any evidence. Or even worse, what if we completely misunderstood how the universe's chemicals came to be? Webb's sensitivity allows us to read the spectral lines of distant galaxies with unprecedented clarity. And those lines tell a chemical story, one that increasingly does not match the predictions of standard Big Bang nucleosynthesis. The deeper we look, the more it seems that metals are baked into the early universe, like ink that appeared in the book before the printing press was even invented. It's not supposed to be this metal-rich, so what should we do with it? We can change the models, imagine the worst possible situations of stars forming quickly, or change the definition of early. But each fix makes a model that was once praised for its beauty even more difficult to use. We could also face a more serious possibility. The universe's chemical past is not clean, straight, or young. Steals, like galaxies and black holes, might be teaching us about something older than the Big Bang, something more in-depth than the timeline we've come to believe. Primordial gas clouds that don't fit the Big Bang. It was thought that the early world would be easy. As the universe slowed down after the Big Bang, it turned into a huge, dark sea of neutral hydrogen and helium. These are the lightest elements that were made in the first few minutes of cosmic nucleosynthesis. It was hundreds of millions of years before gravity brought these elements together to form the first stars and galaxies. During that time, neither fusion nor star death happened to them. The cosmic dark ages were supposed to be a time when nothing was changed chemically and everything was quiet. But now, thanks to the James Webb Space Telescope and other high-precision observatories, astronomers are discovering primordial gas clouds that don't fit that narrative. These clouds are turning up in the deep past, some more than 12 billion light-years away, and they exhibit properties that challenge nearly every assumption about the early universe. Their temperature, composition, structure, and density all raise uncomfortable questions. First, there's the issue of metal content. Some of these gas clouds, supposedly untouched by star formation, already show signs of contamination by heavier elements like carbon, silicon, or even iron. These metals should not be there. According to the standard Big Bang model, the only way to produce these elements is through the lives and deaths of stars. If these gas clouds are truly primordial, then they should consist solely of hydrogen and helium. Their unexpected metallicity suggests they've either been polluted by an earlier generation of stars we haven't accounted for, or they predate the timeline we've constructed altogether. Second, their density and temperature seem off. Some of these clouds are cooler than expected, indicating a level of thermal stability that shouldn't exist so soon after the formation of the universe. Others are hotter and denser, raising the possibility that some form of unknown energy or pressure is acting on them. This opens the door to more exotic explanations, like primordial magnetic fields or residual heat from a previous cosmic cycle, both of which fall outside the standard Big Bang toolkit. Then there's their structure. In the early universe, gas was supposed to be more or less evenly distributed, disturbed only by tiny fluctuations imprinted during inflation. But some of the gas clouds Webb and other instruments are detecting appear to be filamentary, clumped, or even rotating, as if they're already on their way to forming galaxies. That structure should take time. It should be the result of gravitational evolution, and yet it seems to be there from the beginning. Either the physics of gas collapse and star formation are more aggressive and efficient than we've believed, or these clouds are not as young as their redshift suggests. Some scientists are beginning to wonder whether redshift-based dating, the idea that higher redshift equals older light, might be misleading us when it comes to these particular phenomena. Could some of these gas clouds be closer in time than they appear, perhaps distorted by effects we don't yet understand? Also, it's interesting to note that these clouds are in an odd place. They don't always match up with known formations in the galaxy. Some show up in empty spaces. Others are not connected to any star-forming areas that can be seen. Because they are so far away, it's hard to say what kind of thing they are. Are they lost galaxies, proto-galaxy halos, or remnants from a past hidden period of cosmic evolution? One very scary idea is that some of these gas clouds are leftovers from an earlier universe. They could be the pieces of a cosmic cycle that finished in collapse and began again. In circular or bounce models, pieces of a previous world could live on and change how the next one works. So these clouds wouldn't just be strange, they would be signs, chemical and structural traces of a universe that died so that ours could begin. Mainstream astrophysics isn't ready to go that far, but the growing pile of inconsistencies can't be ignored. These gas clouds defy categorization. They're not pristine, not uniform, and not passive. They seem to know more than they should, to have histories before the story officially began. In the standard model, everything builds upward from simplicity. First hydrogen, then stars, then galaxies, then complexity. But these gas clouds seem to invert that ladder. They arrive already shaped, already enriched, already influenced. And that forces us to ask, what came before the beginning? Alien civilizations and the Fermi paradox. Scientists, thinkers, and people who just like to look at the stars have all been troubled by the same question. Where is everyone? This is what the Fermi paradox is all about. The strange difference between the high chance of alien civilizations and the complete lack of sound we hear. Each galaxy has billions of stars, and many of them are much older than the Sun. This means that intelligent life should have had plenty of time to develop, spread, and leave a mark that can be found. Still, nothing. With James Webb piercing the veil of the early universe and revealing mature galaxies, advanced structures, and signs of early complexity, the Fermi paradox takes on a darker, deeper dimension. Because if the universe formed organized structures earlier than we expected, then intelligent life, at least the potential for it, may have had a head start by billions of years. The information from Webb shows that galaxies and stars are forming very quickly, even in the very first few 100 million years after the Big Bang. That means planetary systems might have formed a lot earlier than our models suggested, bringing with them the chance of places where people could live. It's possible that societies rose and fell before Earth even cooled down, if it's a late starter in the history of the universe. The Fermi equation has been changed. We no longer wonder if there is life somewhere else. It's possible that civilizations had a lot of time, maybe even eons of time, to grow, spread, and even go beyond biology. So the silence isn't because there aren't any chances. This is a sign that something much deeper, or even scary, is going on. There's a chance that we're not really alone, but just separated. Dark energy is speeding up the growth of the universe, which means galaxies are moving farther away from each other all the time. It's not only not possible to communicate, move, or be detected over very long cosmic distances, it's physically impossible. Civilizations may have lived and even thrived, but the very structure of space kept them from spreading. Another chilling possibility, civilizations don't last. The same evolutionary shortcuts that allow galaxies to mature early may also set the stage for rapid self-destruction. If early intelligent life existed, it might have annihilated itself long before developing interstellar communication. The more advanced a civilization becomes, the more capable it is of engineering its own extinction, whether through war, artificial intelligence, or environmental collapse. There's also the unsettling idea that civilizations transcend before they reach out. Advanced beings may abandon physical reality altogether, migrating into digital substrates, quantum matrices, or artificial universes, simulated realms where they no longer interact with the observable cosmos. To them, the universe we see might be irrelevant background noise, like a forgotten wilderness outside a digital metropolis. Webb's revelations don't disprove any of these scenarios. Instead, they make them more plausible. By showing us a cosmos that reached structure and complexity sooner than expected, it opens the door to a longer timeline of life, and by extension, a longer history of silence. Then there's the really serious thought. What if other cultures do reach out, but we're still too simple to notice? It's possible that the signs of intelligence are not radio waves or huge buildings, but rather small changes in quantum entanglement, gravitational lensing, or the cosmic background itself. Given that we don't fully understand what Webb is showing us about the world, how could we possibly recognize the work of minds that are billions of years away? There is also a last, more positive view. It's possible that we haven't heard from aliens yet because we are the first ones to arrive. Not just one, but the first people to live in a world that is still young and waking. The things Webb found may point to early organization, but they don't prove that life existed. Maybe it's not often that worlds with stable, carbon-rich surroundings are good for life. Maybe ability isn't a given, but rather a rare thing, and we, being strange and weak, could be the first voice in a very quiet universe. Our voice could either become lost in space or begin a talk that will last a very long time. Did the universe begin at all? The idea that the world had a start is one of the most important ideas in modern science. The Big Bang was a single, powerful event that caused all of time, space, and matter to burst forth. It made a space clock for us, a place to start, a way to ground life in a timeline that we could study, break down, and model. We can now talk about this question that used to be private. It makes sense. Further Webb looks into space and time, the more it shows a world that doesn't look like it was just made. Instead of seeing galaxies coming together, we're seeing structures that are already set up, stars that are already full of metals, and black holes that are already firmly rooted in the centers of galaxies. It doesn't look like the beginning of anything. It looks like something is still going on. In classical physics, the idea of a beginning creates a boundary, a place where our laws break down. The Big Bang singularity is that limit, infinite density, infinite temperature, and no explanation beyond it. Time starts at zero. There's no before. But that's not science. That's an admission of ignorance wrapped in mathematics. Alternative models, once pushed to the fringes, are now crawling into the spotlight. Some cosmologists argue that the Big Bang wasn't a beginning, but a phase transition, like water freezing into ice. The universe may have emerged from a previous state, one we can't yet measure, where quantum fields or higher dimensions existed in a different form. Others suggest the universe never had a beginning at all, but is eternal, cycling through bounces, contractions, and rebirths without ever truly stopping or starting. There's also the growing body of quantum gravity research, which hints that time and space themselves may be emergent properties, not fundamental ingredients. If that's true, the idea of a beginning becomes meaningless, like asking when the surface of a lake began, while ignoring the molecules underneath. What's pushing these ideas forward is not just theory, but evidence that doesn't fit the traditional Big Bang model. The galaxies James Webb sees are too developed, too massive, and too chemically evolved for a universe that's supposed to be in its cosmic infancy. The structures in the cosmic web are too organized. The stars are too mature. These don't just strain the timeline, they suggest that the timeline itself is broken. But what would it mean for the world to not have a beginning? It could mean that the universe is an endless engine that changes shapes and has no real beginning. It could mean that time as we know it is just an illusion in one place, and that reality as a whole doesn't follow a strict timeline. Some very extreme ideas even say that the universe might be a block that doesn't move. In this case, the past, present, and future all exist at the same time, and our sense of a beginning is just a result of how we look at things. An old philosophy debate is brought up again by the idea that the world might not have started. Is the idea of creation necessary? Is life itself a case of causality? Or are we like fish in water, unable to see the ocean around us, forced to believe in starts and ends because that's how our minds are wired? This doesn't mean that the Big Bang is over. It is still the most reliable model we have for many things about the universe, like the CMB, the growth of space, and the fact that there are a lot of light elements. Which makes us wonder, is the Big Bang the beginning, or is it just the start of what we can see? Philosophers in the past thought that the universe was timeless and a perfect machine that never changed. Then there was the Bang, which brought the idea of birth into the universe. But maybe we're back where we started. It's possible that the world never began. It could have always been that way. Rethinking space-time is our model of reality broken. We've used Einstein's model of space-time for more than 100 years. It describes a four-dimensional cloth where mass bends space, space tells matter how to move, and time keeps ticking forward like a cosmic clock. It's amazing how well this model has worked. It said black holes would happen. It said gravitational waves would happen. It's helped us make maps of galaxies, models of paths, and even very accurate guides for spaceships traveling through the solar system. But now, as James Webb opens our eyes to the farthest reaches of the universe, a deeper, more troubling question is surfacing. What if space-time itself is the illusion? Because the more we look, the more the universe begins to defy the geometry we thought it lived in. From galaxies that form faster than space-time allows, to stars that mature before time should have given them permission, we're seeing behavior that doesn't quite fit the model. And at the foundation of this growing tension is a radical idea emerging from the world of quantum physics. Space and time may not be fundamental at all. In this view, what we perceive as space and time might be emergent phenomena arising from a deeper layer of reality, like temperature emerging from the collective motion of molecules, or a hologram forming from interference patterns. Time may not flow. Space may not stretch. Instead, both could be coarse-grained perceptions, byproducts of something we don't yet have the language to describe. This is more than just philosophical speculation. It comes from real theories, such as causal set theory, emergent gravity models, and loop quantum gravity. These ways of looking at things suggest that space-time is made up of smaller, more basic parts, like tiny bits of quantum information that are linked across a deeper layer. And when the James Webb satellite shows us a world that acts like structure came before distance, or memory came before age, it makes us wonder if we're really seeing space and time, or just bugs in their code. It's even against the law to talk about space. Redshift, which is the main way we figure out how far away something is based on the idea that space expands over time. But if that stretching isn't real or isn't constant, then our whole idea of how big the universe is might be wrong. It's possible that galaxies that we think are 13 billion light-years away are actually closer than we think. They could also be somewhere else, not in space in the usual sense. Consider entanglement, a quantum phenomenon where particles separated by light-years act as if they're side by side. Some physicists believe this isn't just a weird trick of the quantum world. It's a hint that distance itself is a kind of illusion, that two points can be close in a deeper information-based reality, even if they're far in ours. If that's true, then space may be relational, not absolute, and the structure of the universe may depend more on connectivity than on coordinates. Time fares no better. In classical physics, time is absolute. In relativity, it's elastic, dilated by gravity and velocity. But in quantum physics, time is almost an afterthought, not a fundamental variable, but a parameter imposed by the observer. In some formulations of quantum gravity, time doesn't even exist. Things just are, and what we call change or causality is a kind of narrative we impose on a timeless web of relationships. If Webb scans keep showing galaxies acting like time began before it should have, or space was organized before it could have evolved, we might need to think about a universe that isn't just old, fast, or strange. We might need to think about a universe that doesn't use space-time at all. The catch is that we may already be able to see the cracks. People are becoming more interested in the holographic principle, which says that all the knowledge in the world might be stored on a flat surface. Quantum entanglement, black holes, and even dark energy may all be signs that we're living in an imagined world where space-time is just a trick and information is the real currency of the universe. quantum gravity, and the early universe. We know about gravity longer than any other force in the universe. Newton described it with apples and circles, and Einstein changed it with space-time curves. Galaxies are held together by it, black holes are made of it, and planets and stars move around as they dance. But gravity is still a strange thing in the world of science, despite how big it is. Unlike the quantum forces, electromagnetism, the strong force, and the weak force, gravity resists unification. It doesn't play well with the rules of the quantum world, where uncertainty, entanglement, and probabilities reign supreme. And nowhere is this mismatch more urgent than in the moments just after the Big Bang, or whatever primal event our universe emerged from. James Webb may not directly detect quantum gravity, but its discoveries are now pushing scientists to revisit this elusive frontier. The telescope's observations of galaxies forming too early, stars enriched too quickly, and structures appearing without the expected scaffolding of time and space all suggest that something deeper, a more fundamental law of nature, may be at work. Something that only a theory of quantum gravity can explain. At its core, it's the effort to reconcile general relativity with quantum mechanics, to describe how gravity works when things are extremely small and incredibly energetic, such as in the first instant of the universe or inside black holes. But traditional physics breaks down in these extremes. General relativity predicts smooth spacetime. Quantum mechanics predicts fluctuations, uncertainty, and discrete bits of information. Combine the two and you get mathematical chaos, infinities, nonsensical results, and models that implode. Builders are making brand new systems from scratch to fix this. String theory says that particles are not points, but strings that vibrate and live in up to 11 dimensions. If the extra dimensions are buried or squished together, these strings can bring together all the known forces, even gravity. String theory even accounts for branes, which are higher dimensional walls that could hold whole worlds. This is where concepts like the universe and cyclical cosmos grow. Loop quantum gravity, LQG, on the other hand, goes in a different direction. Space is broken up into separate pieces, like dots on a computer screen. LQG says that space is not a single block, but rather a grainy mesh made of tiny loops of quantum information. Like this network, time is no longer a smooth flow. It changes as the network does. One of the most important things it means, that the Big Bang wasn't the start of something, but rather a quantum bounce, a change from a universe that was squeezed into a small, non-singular state. These aren't just weird math games. Real tests can be done on them, and James Webb may be moving us closer to those tests. As an example, if space and time come from quantum processes, then the early universe should have quantum fingerprints, such as changes from being smooth, strange structures forming, or strange ways that light travels. Some of Webb's finds, like galaxies that don't seem to follow the rules for how fast structures form, could be these kinds of hints. Even the supposed uniformity of the cosmos, once attributed to inflation, could find alternative explanations in quantum gravity. In some models, quantum entanglement across pre-spacetime could account for the deep coherence of distant regions of the universe. These models suggest that causality, as we understand it, may not have applied during the earliest epoch. Everything could have been linked in a pre-geometric state where distances didn't yet exist. One of the most important effects is the idea that information is more basic than matter or energy, and that patterns of quantum entanglement may even shape the shape of spacetime itself. From this point of view, the universe isn't something that's spreading through space. It's a computer, a huge quantum network that turns data into experience. So when James Webb looks back into the past and finds galaxies that are already fully formed, or black holes that are too close to the start of everything, it's not always a problem with the camera or the data. In this area, space, time, and gravity are not the rules, but the effects. It could be a glimpse into the quantum roots of reality. The holy grail of physics has long been the theory of everything, one formula to unite the cosmos. But perhaps what we need is not a single theory, but a paradigm shift, a new way to see the universe not as a place governed by forces, but as a process unfolding from the quantum fog. A place where beginnings are illusions, and gravity is not a cause, but an echo. James Webb and the death of the Standard Model of Cosmology. This model, called the Standard Model of Cosmology, or KCDM, lambda cold dark matter, has been the most important thing in modern astronomy for many years. According to this theory, the universe began with the Big Bang. It also describes the early stages of inflation, the creation of the cosmic microwave background, the spread of galaxies, and the unknown dark ingredients, dark matter and dark energy, that shape the universe. It looks classy, able to guess. It's a type that has held up through many tests. The Standard Model was always a best fit theory, a patchwork of observations retrofitted into a coherent narrative. It made bold assumptions that space-time is smooth and homogeneous on large scales, that gravity governs structure formation, that redshift directly measures distance and age, but it also carried deep mysteries. What is dark matter? Why is dark energy accelerating the universe's expansion? What happened before inflation? It worked, but only by asking us to believe in things we couldn't see, define, or fully test. The telescope has found galaxies that are too old, too massive, and too organized to exist at such high redshifts. According to the Standard Model, the early universe was a chaotic soup of particles slowly cooling and clustering. It should have taken hundreds of millions, if not billions of years, for galaxies to take on the size and structure Webb is now detecting, just 200 to 300 million years after the supposed beginning. This mistake is pretty big. It's not a change. It's a break, which means that the model's basic ideas about time, matter, and energy might not be true anymore. The timetable is wrong. The buildings aren't ready yet. Now it seems like the equations that led us here were never meant to explain this part of reality. Even scarier is the fact that cosmic factors are becoming more tense. The Hubble constant, which counts how fast the universe is expanding, gives different answers based on whether it comes from observations of the early universe, like the CMB, or from nearby galaxies, like the ones Webb is looking at right now. The difference between them is getting bigger, not smaller, which makes it possible that we are not even measuring the same world. These problems aren't just observational. They strike at the conceptual core of the Standard Model. If galaxies form faster, if time behaves differently, if redshift isn't a reliable clock, then the foundations of LCDM begin to tremble, and scientists are taking notice. Some researchers say Webb's data might mean we need a whole new theory of the universe, one that doesn't just fix the old one, but builds it from scratch. That could mean moving away from a model of the universe where dark matter and general relativity are the only laws that rule it, and toward one where quantum information, emergent spacetime, or physical laws that we don't know about take center stage. Some people think we might need to look at old data in a new way. It's possible that our predictions were wrong if Webb shows us a world that doesn't match what we thought it would be like. The cosmic microwave background has been thought to be the best picture of the early universe for a long time, but maybe it is being read wrong. It's possible that dark matter is not a particle but a field or a result of forces that can't be explained. Maybe dark energy isn't really growing the universe. Maybe space is changing in a way we haven't thought of yet. This isn't a rejection of science. It's science doing what it's supposed to do, confronting the unknown and refusing to look away. The Standard Model served us well. It got us to the moon and beyond. But models aren't meant to last forever. They are tools, not truths. And when the tools stop fitting the data, it's time to invent new ones. How the scientific community is reacting. When the James Webb Space Telescope sent its first pictures back to Earth, most scientists were expecting a few shocks, like better pictures, deeper insights, and maybe even some changes to the timeline of the universe. What they didn't expect was a rising number of finds that would shake up modern cosmology from the ground up. As early findings came in, including galaxies that were too massive to be possible, structured clusters that formed too soon after the Big Bang, and black holes that formed faster than models suggested. Scientists had mixed, sometimes nervous, and often deep thoughts. In the halls of research institutions and the pages of scientific journals, one thing became clear. Webb wasn't just revealing the universe, it was revealing the limits of our understanding. Many cosmologists responded with a mix of awe and disbelief. For some, the findings were exhilarating. After decades of working within the constraints of LCDM, they saw Webb's anomalies as permission to rethink, to question assumptions that had grown too comfortable. "We've been given the chance to rewrite cosmology from the ground up," one astrophysicist wrote, "and we'd be fools not to take it." Others reacted with caution, or even resistance. The Standard Model has earned its place through decades of predictive success. It elegantly accounts for cosmic background radiation, large-scale structure, and the abundance of light elements. For these scientists, anomalies aren't a reason to abandon the model. They're a reason to refine it. Perhaps star formation in the early universe was more efficient than we thought. Maybe dark matter played a bigger role, or inflation worked differently. Rather than a revolution, they see evolution, a few tweaks, not a teardown. And in truth, science is not built on dramatic overthrows. It's built on slow, methodical correction. Paradigms shift not in headlines, but in footnotes, conference talks, and peer-reviewed debate. Still, there's a palpable tension beneath the surface. Some researchers express concern that the cosmological community has become too attached to its models, too reluctant to admit when the data no longer aligns. They point to historical moments where entrenched thinking slowed progress: the refusal to accept heliocentrism, the rejection of quantum theory, the initial dismissal of plate tectonics. "We're seeing the same pattern," one theorist warns. "A model becomes dogma, and dogma is the enemy of discovery." This strain is most clear in the way people talk about science in public. Headlines like "James Webb could rewrite cosmic history" or "The Big Bang under fire" now appear on articles that used to praise the Standard Model. Astrophysicists argue about redshift readings and the early stages of galaxy creation on social media in the same way that philosophers argue about the nature of time. Some people enjoy the chaos. Others call for moderation. A lot of people are arguing, and the talk is often very honest. Part of the disagreement comes from the fact that Webb's data is so new. It's never happened before. We're seeing parts of the universe we've never seen before, and with a level of detail we never thought possible thanks to ultra-deep infrared images. We don't know yet if the strange things we're seeing are real or if we're misunderstanding them. There is still a chance of calibration mistakes, unknown observational biases, and reading errors. Multiple teams, using independent methods and instruments, are verifying similar results: early galaxies that break formation models, redshifted light that raises uncomfortable questions, black holes that seem to skip evolutionary steps. As these patterns harden into confirmed facts, a new generation of physicists is stepping forward. Researchers less wedded to the old ways, more comfortable navigating the unknown. For them, Webb's revelations aren't a crisis. They're an invitation to explore new ideas, resurrect discarded theories, and build models that reflect a universe that may be stranger, older, or deeper than we dared to dream. Some people are looking again at strange ideas like tired light, plasma cosmology, and bouncing universes. Some people are working on quantum gravity models that get rid of the singularity and break space-time up into networks of entanglement and information that are based on probability. What was pushed to the edges is now getting attention, but not as solutions. Instead, it's being talked about as fair questions. However, words that say, "we don't know," are the most honest. Because science isn't really about protecting what we know. It's about being brave and curious about what we don't know. And James Webb is better than any other tool in history at doing that job by showing us what doesn't fit. Big Bang loyalists, defending the Standard Model. To them, the Big Bang is not just a theory. It is a battle-tested framework that has survived one of the most demanding gauntlets in all of science: prediction, observation, and repeatability. The Standard Model successfully predicted the cosmic microwave background long before it was discovered. It explained the abundance of light elements in the early universe. It accounts for the expansion of space, the formation of large-scale structure, and the growth of cosmic voids. These are not small victories. They are monumental achievements that earned the model its throne. So when James Webb unveils galaxies that appear more mature than expected, or black holes seemingly formed too quickly, loyalists don't panic. They analyze, they adjust parameters, they explore the margins of existing theories. One common defense is that Webb is showing us not the average galaxy at a given redshift, but the exceptional ones, the statistical outliers that formed earlier or evolved faster than the norm. Another explanation centers around selection bias. Perhaps we are currently seeing only the brightest, densest galaxies because those are the easiest to detect with infrared instruments. As Webb continues to collect more data, including fainter, more typical galaxies, the apparent anomaly might dissolve into a more familiar cosmic pattern. Then there's the question of dust and lensing. Material between the stars and gravitational effects could be changing how old and bright these galaxies look. It's possible that these affects will make them look older, bigger, or more organized than they really are. Some supporters say that what we're seeing might not be a problem with the Standard Model, but an incorrect reading of the signs. One more point is based on practicality. Even though it has problems, the Standard Model is still the best way to study and understand the universe. It doesn't have to be thrown away completely. It can be changed. For example, new types of dark matter, better inflationary models, or early explosion processes could be added. This way of thinking is similar to how Newtonian physics gave way to relativity, not by rejecting it, but by incorporating it into a bigger picture. Loyalists also point to the danger of what they call anomaly hunting, the tendency to latch onto unexplained data points and build entire alternative frameworks around them. Anomalies, they argue, are not new. The history of cosmology is full of them, and most have found their place within the prevailing model once more data arrived. Science doesn't move on excitement alone, one cosmologist wrote. It moves when consistency breaks across the board. That hasn't happened yet. It's a valid stance. Paradigm shifts in science are rare, and they're only justified when no amount of adjustment can reconcile the old model with new observations. As of now, many Webb findings, while shocking, haven't yet reached that critical threshold. And in the eyes of Big Bang loyalists, until that happens, the burden of proof lies with the challengers. But perhaps what's most admirable about the loyalists is not their adherence to the Big Bang, but their insistence on rigor. The scientific method demands skepticism, not just of new ideas, but of ourselves. It's easy to be seduced by revolution. It's harder to hold the line until the data is airtight. But even followers are becoming more and more aware that the plan needs to change. Not many people disagree that what Webb found is strange. Most people agree that something new is coming, whether it's new information about how stars form, a new way to look at redshift, or the first signs of a theory that was once thought to be unbreakable. So the commitment isn't to theory but to method. The Big Bang is still the default because it works. But if the day comes when it doesn't, when the evidence calls for a different story, even the most devoted supporters know what they have to do. Radical new models being proposed. Science doesn't fall apart when the foundations of a theory start to shake. Instead, it changes. Since James Webb's discoveries that seem to go against everything we know about the world, there has been a quiet but rising revolution in theoretical physics. More and more cosmologists are looking to bold new models of the universe that change the rules from the very beginning. These models used to be on the edge because they go against what we know about the universe's history. Among the most talked about is the Big Bounce model. Rather than a universe born from a singular explosive beginning, the Big Bounce proposes that our cosmos is the latest in a cyclical series of universes, expanding, collapsing, and rebounding over and over through infinite time. In this view, the ultra-early galaxies seen by James Webb aren't premature. They're leftovers, remnants of a prior cycle's end. Gravity compresses the universe until it rebounds into a fresh expansion. There's no beginning, just transformation. Roger Penrose, a Nobel Prize winner and one of the most recognized minds in modern physics, came up with conformal cyclic cosmology, CCC. This model says that the conditions at the start of a new universe are exactly the same as those at the end of an old one. This is because expansion stretches the old one so far that everything breaks down into massless particles. There is no boom as one eon ends and the next one begins. Webb's finding of strange order in the early universe could be seen as information from a different time in the universe leaking through. Emergent space-time models are getting more and more attention. In these models, space and time are not basic at all, but instead come from quantum information structures. These ideas say that the world works like a computer program. Entanglement and the flow of information cause things like distance, time, and gravity. It's not that the timeline is broken, it's that our sense of time is wrong. Some forms of this theory say that the early universe looked fully formed because space-time came into being all at once, like starting up a game. In the more speculative corners, we find theories like plasma cosmology, which rejects expansion entirely. It proposes that the universe is an immense, stable structure shaped by electromagnetic forces, not gravity and dark energy. In this view, redshift isn't due to expansion but to energy loss through interaction with the intergalactic medium, a revival of the tired light hypothesis. While controversial and often dismissed by mainstream astrophysics, plasma cosmology has gained renewed interest due to Webb's challenges to traditional expansion metrics. The universe made of holograms. This model is based on string theory and black hole physics. It says that everything we see as three-dimensional is actually stored on a two-dimensional border. The world is not growing bigger in space. Instead, it is moving forward from a surface of quantum data. It's not a bug in this model for early galaxies to form in fully grown states. It's how information unpacks across the hologram screen. Some very extreme models even go after the holy principles of nature. Some scientists are looking into whether things like the speed of light or the gravitational constant may have changed over time, which would have had a small effect on how the universe formed in the beginning. In that case, things we think of as strange could be proof that the world used to follow a different set of rules when it was first formed. Still others believe we may be living in a multiverse, and our corner of reality simply reflects unusual initial conditions. What seems improbable from our perspective might be common somewhere else. In these models, early galaxies, strange redshift behavior, and mature stars are features of a localized cosmic bubble, not failures of a universal law. These ideas don't have the same structure, but they do have the same spirit, cosmic humility, the understanding that the world doesn't have to work the way we want it to, and that sometimes we need to see things in a different light to find the truth. Radical models do, of course, come with risks. They are usually less beautiful, harder to test, and quickly thrown out as theoretical. But they also make the discussion bigger. They make it possible to do new math, make new discoveries, and think about old problems in new ways. Philosophical implications. What if the universe had no beginning? Since the beginning of time, people have looked up at the sky and asked, where did all this come from? Every culture has its own story about how the universe came to be, from gods making the world to machines calculating space and time. There is still a story behind modern science. Even though it is based on data, the world was born, it grew and changed, and now we are here to ask about it. This isn't just a scientific dilemma, it's a philosophical upheaval. A universe with no beginning challenges our most basic frameworks of causality, purpose, and meaning. After all, we're creatures of narrative. Our brains are wired to think in arcs, starts, middles, ends. Even our personal lives are structured that way: birth, life, death. So when cosmology threatens to remove the birth from the universe itself, it's not just a physics issue, it's an existential one. At the heart of the Standard Model sits a moment called t equals 0, the singularity. It's the supposed beginning of time and space. But if Webb's discoveries suggest that structure, matter, and even mature galaxies were already in place before what should have been the opening scene, then our concept of a starting line dissolves. There are a lot of philosophical effects that come from this. One reason is that it changes the idea of first cause, which has been important in philosophy and religion for thousands of years. The idea that everything must have a beginning is at the heart of many arguments for the presence of a creator, such as Aristotle's unmoved mover and the standard cosmological argument. That chain is broken if the universe has always been there. There was never a first result, so there is no need for a prime cause. This could either threaten or liberate theological thinking. Some traditions may resist the idea, clinging to a creation event as proof of divine action. Others might embrace a more timeless, omnipresent concept of divinity, one not confined to a beginning, but embedded in the eternity of existence itself. Then there's the question of meaning. In a universe with a beginning, we can imagine a direction, a purpose or trajectory that starts with creation and moves toward complexity, life, maybe even consciousness. But if there's no beginning, then perhaps there's also no intended direction. We are not a culmination. We are just a moment in an infinite chain of cosmic fluctuation. This might feel bad, but it can also make you feel free. It means that the world doesn't have a built-in meaning. It's something we make. In a universe that will never end, our job is not to follow a plot that has already been written. It's to write our own meaning over and over against the universe's lack of interest. There's also the issue of time. Kant and other philosophers said that time is not something out there, but something that our minds make it so. If the world doesn't have a start, then time might not be very important. Some scientists already say that time is emergent, meaning that it comes from quantum systems or thermodynamic patterns that are intertwined. For this point of view, the beginning is not a real event, but a point where our understanding ends. That brings us to what may be the scariest implication. Our questions may not be right. If the world has always been there, then maybe asking when it started is like asking what's north of the North Pole. It's not a good use of language or logic. Maybe our desire to know where we came from is just a result of living in time, and not a picture of how the world is really put together, not in chaos, but in a deeper sense of respect. James Webb is more than a telescope. It's also a screen. It shows both the early light of the universe and the limits of what people can understand. It shows us that even the most important ideas we hold dear, like starts, causes, and arcs, may just be small-town comforts. Future missions after James Webb. Webb is not the end, even though its findings have changed the way things are thought about. There will be a fleet of next-generation projects that will go even deeper, wider, and stranger than ever before. This is the start of a new era in science. A lot of people are looking forward to NASA's Nancy Grace Roman Space Telescope, which is set to launch later this decade. People often say that Roman will have a field of view 100 times bigger than Hubble's and the same level of sharpness, which will make it perfect for seeing huge areas of the sky in great detail. Webb looks very deeply and narrowly into the past. Roman, on the other hand, will map the structure of the universe on very large scales, keeping track of how galaxies group together and how dark energy affects the speeding up of the universe. Where Webb points out the weirdness, Roman will measure how strange it is and decide if oddities are random events or systemic flaws in our understanding. On the ground, the Vera C. Rubin Observatory in Chile, scheduled to begin full operation soon, will conduct the Legacy Survey of Space and Time, LSST. This ambitious 10-year program will catalogue billions of galaxies, track transient events like supernovae and asteroids, and create a motion picture of the dynamic universe. Rubin's strength isn't depth, it's motion and pattern, giving us time-based insights to match Webb's snapshots. If the early universe was more chaotic, faster evolving, or discontinuous than we think, Rubin will be the observatory to catch those subtle temporal fingerprints. Meanwhile, Europe's Euclid mission, launched by ESA, is already scanning vast regions of the cosmos to study the mysterious fabric of dark energy and dark matter. While it may not match Webb's infrared sensitivity, Euclid complements it by focusing on gravitational lensing, how light from distant galaxies is warped by massive structures. This will help scientists test whether general relativity itself breaks down at cosmic distances, potentially replacing Einstein's theory with something more exotic. The Extremely Large Telescope, ELT, is a huge structure being built on the ground in the Atacama Desert. The ELT will be able to directly view the first stars and exoplanets thanks to its 39-meter mirror, which is the biggest of its kind. This will allow for spectroscopy of ancient galaxies that has never been done before. It can be improved and kept up to date, unlike space telescopes, which makes it a long-term watchdog for finding the quantum and chemical signatures of cosmic structures that don't fit with current models. In the far future, NASA is working on LUVOIR, which stands for Large Ultraviolet Optical Infrared Surveyor. This is an idea project that will be much more powerful than Webb. LUVOIR is meant to look into everything, from how life began on faraway exoplanets to the most mysterious objects in space that are hiding in plain sight. If it were to be launched, LUVOIR would be the most powerful all-purpose space telescope ever made. It could also be the best way to find out if the universe had a beginning at all. And beyond LUVOIR, even stranger concepts are being developed. Missions like LISA, Laser Interferometer Space Antenna, will detect gravitational waves from space, opening a new sensory channel for understanding how black holes merge and possibly how the universe vibrates at its deepest frequencies. Gravitational waves offer clues that light can't, and may reveal ripples from events before light itself could travel. As the boundaries between astrophysics, quantum theory, and cosmology blur, future missions may not even resemble traditional telescopes. They might be swarms of satellites forming artificial interferometers. They might utilize quantum sensors to detect minute curvature shifts in space-time. Or they might attempt to study neutrino backgrounds or relic gravitational radiation from hypothetical pre-Big Bang states. The media versus the reality, misreporting the death of the Big Bang. Nuance is good for science, but the internet loves uncertainty, strife, and things that you can click on. The James Webb Telescope really only showed strange data, galaxies that looked too big, too old, and too structured for their redshift. These results make us think about our theories of the universe in a good way, but they don't kill the Big Bang any more than early airplane crashes killed the idea of planes. A lot of the experts who were quoted in these popular pieces were actually misquoted, misread, or made to sound more important than they really were. To the trained cosmologist, phrases like, "The universe is older than we thought," or "The Big Bang is in crisis," must be handled with extreme care. The Big Bang is not simply a single event. It's a model based on a framework of tested observations. The expansion of space, the cosmic microwave background, the abundance of light elements. These observations still hold. James Webb hasn't invalidated them. What it has done is reignite debate over what happened immediately after, and how the earliest structures formed. But in the media, subtle challenges to early universe structure formation quickly morphed into declarations that the Big Bang was dead. This is a pattern that has long plagued science communication. A single anomaly becomes proof that everything we know is wrong. A cautious quote becomes a clickbait headline. The scientific method, built on slow refinement, peer review, and cautious interpretation, gets replaced by spectacle. Even worse, this disconnect has real-world consequences. It fuels public misunderstanding, polarizes discourse, and sows distrust. To someone reading the news casually, the constant swinging between science proves everything and science is completely wrong creates the illusion that science is just guessing, that it's fragile, that it flips with every new photo. But in reality, science is resilient by design. Theories are not sacred texts, they are tools. And when those tools no longer fit, They get sharpened, adjusted, or replaced. What James Webb is doing is exactly what any good scientific instrument should do: challenge the comfort zone, expose blind spots, and sharpen our questions. It's important to remember that many scientists are excited by these anomalies, not because they want to throw away the Big Bang, but because they finally have fresh tension to explore. For years, cosmology had grown complacent. The standard model explained most things well enough, but Webb cracked the sky open again, and with it, the possibility that something deeper is waiting underneath. But the public deserves better than oversimplified battles between Big Bang dead and Big Bang lives. They deserve to know that this is not a war. It's a conversation. One filled with disagreement, yes, but also rigor, collaboration, and humility. The scientific community isn't divided into heroes and villains. It's filled with people trying to understand something bigger than any of us can grasp alone. There are scientists actively defending the standard model. There are others proposing radical alternatives. And there are many more asking whether the data itself is incomplete, whether dust, lensing, or redshift interpretation may be throwing us off. All of them are working from the same shared foundation: curiosity and evidence. A new golden age of cosmology? Are we in the beginning of a new era of great cosmology? The last time physics changed this much was in the middle of the 20th century. It had just been found that the cosmic microwave background exists. Hubble's findings showed that the universe was getting bigger. It was the Big Bang model that beat the steady-state theory. Nothing felt old, broken, or full of possibilities. That was the first golden age. It was then that we could study the world instead of just being amazed by it. What makes this era golden isn't just the technology, though that certainly helps. It's the willingness to reimagine. For decades, the standard model of cosmology served as a safe harbor. But now, scientists are embracing the winds of uncertainty again. They're dusting off forgotten theories. They're proposing fresh models where information, not matter, is the fundamental currency. They're asking whether galaxies formed before physics says they could, and instead of ignoring the anomalies, they're chasing them. New missions like the Nancy Grace Roman Space Telescope, the Vera C. Rubin Observatory, and the Euclid probe are poised to gather data on a scale never seen before. These instruments will map billions of galaxies, track cosmic acceleration, and probe dark energy in ways that will either reinforce or redefine what we know. This is no longer a solo expedition, it's a fleet. Meanwhile, ground-based facilities like the extremely large telescope and theoretical endeavors in quantum gravity and emergent space-time are expanding our reach from both ends, observational and conceptual. Together, these efforts form a network of insight. Each finding cross-validates, challenges, or reframes the others. The result? A feedback loop of discovery that feels exponential. But science growth isn't the only thing that makes this era truly golden. Collaboration across fields, countries, and even thought systems is what it's all about. Philosophers are once again important in talks about science. Mathematicians are trying to write new theories of the universe. AI and machine learning are making it faster to find patterns in cosmic data. And amateur scientists are finding supernovae and exoplanets from their own yards with tools that have never been seen before. This moment feels different because it's not based on fact, but on possibility. What's on the table is more important than models, math, or even binoculars. Many people wonder what the truth is, why we're here, and if our world is the only one. There is no faith. There is only growing shame. Maybe the real sign of a golden age is not having the answers, but being able to ask better questions, questions that no one would have dared to ask a generation ago. Take a moment to think about what this means. Right now, our most basic ideas about the universe are being put to the test not by stories, but by facts. Every new picture might be a test to how we fit into the universe. When scientists have to stand up for what works and accept what doesn't at the same time. A theory ends, wonder begins. The Big Bang theory has been our compass for nearly a century. It gave us a beginning, a framework, a way to understand our place in the cosmos. For generations, it lit the way forward, from Einstein's equations to Hubble's redshift, from microwave background maps to particle accelerators. It taught us to think big, to imagine time as a thread and space as a fabric. It could be the start of something much stronger, because failure isn't what happens when an idea stops. It's the return of being amazed. The moment when we realize the map doesn't match the terrain, and instead of being scared, we feel open to what might be possible. This is the kind of potential that can only happen when we put down old tools and look for new ones. We are in such a moment now. We're confronting the idea that space might not be real in the way we imagine. That time might not tick universally. That the early universe may have skipped steps our physics says are required. That galaxies formed before they were allowed to, and black holes sat at their centers too soon, too large, too perfect. In the past, these kinds of strange events would have caused a quiet discussion in academic groups. Today, though, they can be heard around the world on computers, in classes, on podcasts, and on TikToks. It's no longer just a puzzle in labs. It is ours altogether. Not in having all the answers, but in being willing to stand on the edge of what we knew and say, maybe we were wrong. Space might not be what we thought it was. The beginning might not be a beginning after all. We might need a new language made of quantum threads, emergent rules, or something we haven't even seen yet. The James Webb Space Telescope is more than just a bunch of screens and gold metal. It's like a mirror for our thoughts, something that shows us the world as it really is, not how we think it should be. Messy, beautiful, not finished. And those of us who think, doubt, dream, and ask questions must walk through it. The next thing that might happen might not be a new idea right away. It could be stress, not clear, arguments, years of wrong starts and models that didn't work. But every golden age starts with pain, with what we thought was solid ground breaking apart. We'll start to build again on top of that mess. The James Webb Space Telescope hasn't just given us beautiful pictures, it's also shown us a hole in the oldest story about the universe. Whether the Big Bang collapses or changes, one thing is certain. We are on the verge of a new era in cosmology, where question leads to finding and mystery leads to certainty. If this journey changed the way you think about the universe, don't stop now. Share and subscribe to join us as we go deeper into the questions that make life possible. Because the world and we change together.